Hello there and welcome to Science for Sleep, where questions get comfortable and curiosity takes its shoes off at the door. Tonight's quiet journey begins with something you can't see, can't touch, and probably haven't thought much about today. And yet it's touching you right now. It's in the space between your fingertips and the screen, humming through your walls, whispering through your body and stretching all the way to the sun and beyond. It's electromagnetic fields. Not exactly the stuff of fairy tales maybe, but give it a moment. Because once you start to notice what they are and where they are, you might start to feel like you're living inside a kind of invisible sea. And maybe you always have been. Before we settle in, I'd love to know, just quietly to yourself, where in the world you're listening from tonight. Are you in a city or tucked away somewhere rural? Are there streetlights outside your window or stars? And what time is it for you right now? Because it seems fitting, doesn't it? To talk about invisible fields at this exact moment, while you're gently surrounded by signals, frequencies, and low, quiet energies that no one ever really sees. If that thought feels even slightly comforting or interesting, or just enough to make you exhale a little longer, then feel free to let your eyelids get heavier as we go. And if this ends up helping you sleep before we even get to the real science, well, that's a nice bonus. Electromagnetic fields might sound like a mouthful from high school physics, or something buried in a textbook next to squiggly arrows and equations you never wanted to memorize. But the reality is they're much more intimate than that. They're not just in power lines or science labs, they're part of every breath you take. They're at work when you flip a light switch, send a text, microwave leftovers, or sit quietly thinking with no gadgets in sight. Even your own heart sends out tiny electromagnetic pulses. Not to get too philosophical too soon, but in some very real ways, we are beings made not just of matter, but of fields. And that's what we're going to unravel. Slowly, gently, without any pop quizzes. If you've ever rubbed your socks on a carpet and zapped yourself on a doorknob, you've already met one kind of electromagnetic field. If you've ever held a magnet near a paperclip and felt that invisible tug, that's another. At their core, these fields are what happen when electric charges are in motion. Whenever something charged starts to move, it creates a ripple in the fabric around it. And that ripple, the invisible influence it has on the space nearby, is what we call a field. It's not made of stuff in the usual sense. It doesn't have weight or color or a smell, but it has power. It can push or pull. It can pass through walls. And it can carry information from one place to another without anything needing to travel across in between, at least not in the way we're used to thinking. The light from your screen right now reaching your eyes is part of that field. So is every beam of sunlight, every radio transmission, every signal bouncing between satellites and your phone. But long before we built anything to harness it, electromagnetic energy was already here. It crackled in thunderstorms before anyone named it. It warmed the first sunlit mornings. It danced in the northern lights before anyone had words for the sky. And the more we've come to understand it, the more we've realized that this one force, this one quietly reliable field, holds together more of the world than we ever expected. It can be hard to imagine something you can't see. The human brain is great at visualizing objects, faces, even places we've never been. But when it comes to fields, those invisible patterns of influence that stretch across space, we need metaphors, and while they're never perfect, they help. You might think of an electromagnetic field like the scent of a candle. You can't see it, but it spreads. It affects things nearby. It fades with distance. Or maybe it's more like a breeze that isn't blowing air but a possibility. Or the sound of a bell echoing, not in your ears but in the space itself. Again, none of those are exactly right, but if it helps you hold the idea gently in your mind without needing to grip it too tightly, that's enough for now. For much of human history, we didn't know any of this. The world worked, but the reason stayed hidden. We saw fire without understanding combustion. We used magnets without understanding electrons. We lit candles without knowing that light itself was just another expression of a field. And that's one of the things that makes electromagnetic fields such an inviting topic for quiet exploration. They've always been here, They've shaped everything from the stars to your blanket, and yet they stayed in the background, unnoticed, until the right kind of noticing came along. Eventually, of course, someone asked the right questions. They didn't know they were about to change how we see the universe. They were just curious. They wondered why a compass points north, why certain metals attract, why amber rubbed with fur could move little bits of straw. Small questions, strange effects. But that's where it always starts, with observations that feel too minor to matter until you follow them all the way through. And in time, following them revealed something extraordinary. That electricity and magnetism, once thought of as two separate things, are really just different faces of the same deeper truth. But we'll get to that. Slowly. No need to rush. For now, maybe just let this settle in. The space around you isn't empty. It's not still. It's humming with fields, and even though you can't hear them, even though your hands pass through them without resistance, they're real. They guide the behavior of everything with charge. They shape how light moves. They hold atoms together, and they're right here. Not in a dramatic science fiction way, but in a quiet, factual, gently astonishing way that might just make the world feel a little more connected than it did before. So as your mind begins to soften at the edges, and your thoughts get a little quieter, take a moment to feel the space around you, not as empty, but as full of motion, of patterns, of forces that don't need to be seen to be trusted. Because in this invisible web of fields, you're already a part of the story, and that in itself is a good place to start, Alright, let's step a little closer now. If this were a story about something you could hold in your hand, we'd start by describing what it looks like. Maybe its shape, its color, how it feels to the touch. But electromagnetic fields don't quite work that way. They don't have an edge. They don't sit still. And they don't show up in the same way as a chair or a stone or even a puff of smoke. So instead of pointing at one, we have to ask something simpler. What are they? The best place to begin is with the idea of a field itself. In physics, a field isn't a thing in the ordinary sense. It's a way of describing what space is doing. Imagine you're standing on a hill. You drop a ball and it rolls downward. That slope you see, the way gravity changes from place to place, that's one kind of field. It tells you something about what would happen to an object if it were placed there. An electromagnetic field works similarly, except instead of affecting mass, it affects things with electric charge. If you put a charged particle into that kind of field, it'll feel a push. It'll move, not because something touched it directly, but because the field shaped the space around it. So what creates these fields? Electric charges. More specifically, charges in motion. Whenever you have an electric charge just sitting there, it creates an electric field. That field radiates outward in all directions, and it describes how another charge would feel if it came nearby. The closer you get, the stronger the effect. Now, if that same charge starts to move, if it flows through a wire or arcs through the air, it begins to create a magnetic field too. And just like that, the two parts are linked. Electricity gives rise to magnetism, and magnetism in turn can create electricity. They're not separate forces after all. They're two halves of one system. This connection was first hinted at in the 19th century. Scientists like Hans Christian Ørsted and Michael Faraday noticed that electric currents could influence compass needles, and that moving magnets could cause electric currents to appear in wires. At the time, these seemed like separate curiosities. But slowly, as the evidence built up, something larger came into focus. The realization that these effects weren't just related, they were reflections of the same thing. Later, James Clerk Maxwell brought it all together into one mathematical framework. His equations, quietly elegant and surprisingly compact, described how electric and magnetic fields behave, how they influence each other, and how they can travel through space in the form of waves. That last part was especially significant. It meant that light itself, what we see with our eyes, is just an electromagnetic wave. Not something special or separate, but part of the same system that drives motors, charges batteries, and makes your hair stand on end after pulling off a wool sweater. This insight tied together optics, electricity, and magnetism into a single field theory. And in doing so, it turned light into something new. Not just a phenomenon of sight, but a ripple in the electromagnetic field, spreading out from one point to another, carrying energy as it goes. To understand how those waves work, it helps to picture what's actually changing. A simple electric field points in a direction, say, up or down. A magnetic field also points in a direction, maybe left or right. When you have a wave made of both, they oscillate at right angles to each other. The electric part wiggles one way, the magnetic part wiggles another, and together they form a wave that moves forward, like a thread spinning through the air. And here's the wild part. They don't need a medium to move through. Unlike sound, which needs air, or ocean waves, which need water, electromagnetic waves can travel through empty space. The vacuum doesn't stop them. In fact, it's their natural home. The field isn't a passive thing either. It carries energy and momentum. It can exert pressure. And when it passes through a material, say your skin or the copper coil in a generator, it can stir up movement, excite electrons, or push charges along a path. This is how energy gets from one place to another without anything solid making the trip. It's how your wireless charger works, how antennas send signals, how the sun warms your skin from 93 million miles away. It's easy to forget just how many kinds of electromagnetic waves exist. The kind we call light is just a small sliver of a much broader spectrum. Go to lower frequencies and you find radio waves, used for music, broadcasts, long-distance communication. Keep going and you reach microwaves, like the kind that bounce around inside your oven, shaking up water molecules to create heat. Even lower still, and you hit the faint hum of extremely low frequency fields, used in submarine communication or created by power grids. Now go the other way. Raise the frequency past visible light, and you reach ultraviolet, which gives you sunburns. Higher still, and you meet X-rays and gamma rays, powerful, penetrating forms of radiation that can both help and harm. All of these waves are electromagnetic. What separates them is simply frequency and wavelength. The faster they oscillate, the more energy they carry. The shorter the wave, the more tightly it's packed. But the underlying mechanism is always the same, a self-propagating ripple in electric and magnetic fields, moving at the speed of light, tracing out an invisible pulse through space. That idea, that space itself can carry these waves, was a major leap. Before this, people thought light had to move through something. They imagined a kind of invisible medium called the luminiferous ether, but when experiments failed to find any trace of it, and Maxwell's theory stood strong without it, physicists began to accept that the field itself is fundamental. It doesn't ride on anything. It is the thing. And yet, despite its power and reach, an electromagnetic field is surprisingly fragile in another sense. You can't isolate it or capture it in a bottle. You can't store it the way you'd store heat or pressure. It's always in motion, always influencing, always slipping through the background of other events. It's there when atoms bond, when nerves fire, when lightning branches out across the sky. And even though you can't feel it directly, at least not consciously, you're always immersed in it. This has practical consequences. Devices like electric motors, generators, transformers and sensors all rely on electromagnetic fields. So do cell phones, televisions, and even traffic lights. Without fields, nothing would connect, nothing would signal, nothing would move. And yet, for all their usefulness, we don't see the fields themselves. We see their effects, a needle twitching, a screen lighting up, a doorbell chime. But the field remains invisible, a kind of hidden infrastructure that modern life quietly leans on. And then there's you. The human body isn't just affected by electromagnetic fields, it generates them. Your brain produces electric signals as neurons fire, and those signals in turn create weak magnetic fields. Your heart does the same, with every beat sending out a rhythmic pulse that can be detected by sensitive instruments several feet away. This isn't science fiction, it's medicine. Electrocardiograms and magnetoencephalograms are just two examples of how we measure those signals to learn what's happening inside. The body, in its quiet regularities, becomes a beacon of biological electromagnetism. So when we ask what an electromagnetic field is, we're really asking about the structure of influence in the world. We're asking how energy moves, how charges interact, how light travels. And we're also asking something more subtle. How does the invisible shape the visible? Because from what we know now, the answer is constantly, gently, everywhere. You don't need to see the field to know it's there. You don't need to memorize formulas to appreciate its presence. And you don't need to feel it directly to understand that every moment of your day, from the buzz of an incoming message to the light bouncing off your pillow, is shaped by this one elegant, continuous force, one that's all around you, and also within. So as you continue to settle into rest, let that thought linger. That space is never really empty. That every corner of the room, every inch of your skin, every quiet hum of electricity nearby is part of a field, a presence, not loud or urgent, just quietly essential, something that doesn't ask to be noticed, but always is once you start to look. All right, let's keep going. The story of electromagnetic fields didn't begin with wires or waves or equations. It started with small curiosities, quiet, easily missed events that seemed strange enough to notice but not strange enough to understand, at least not at first. Centuries ago, long before electricity had a name, people were already observing its effects without realizing it. Amber rubbed with fur would attract bits of straw. Magnets, chipped from the earth, would tug at metal with no visible connection. The behavior was there, steady and repeatable, even if the reasons remained hidden. The word electric comes from the Greek word for amber, electron. That soft, warm-colored resin was one of the first materials known to generate static electricity. If you rubbed it, it would build up a charge, and that charge could influence lightweight objects nearby. To the people who noticed it, this was little more than a party trick of nature, like a breeze that only moves certain things. But as the centuries went on and tools became more precise, those simple observations began to gather weight. In the 1600s, a few natural philosophers began to take a closer interest. William Gilbert, physician to Queen Elizabeth II, wrote a book called De Magnete, where he carefully described the behavior of magnets and compared them to the Earth itself. He suggested that the planet might act like one giant magnet, which was a bold claim at the time. Still, his ideas weren't quite enough to link electricity and magnetism into a single system. That connection would come later. In the early 1800s, Hans Christian Ørsted made a discovery that seems small by modern standards, but was revolutionary in its implications. While setting up a classroom demonstration, he noticed that a compass needle near a wire would move when the wire carried a current. This was the first direct evidence that electric currents produced magnetic effects. It wasn't just that electricity and magnetism were related. They could influence one another, and possibly more than anyone had realized yet. Ørsted's observation was picked up quickly by other scientists. André-Marie Ampère began experimenting with current-carrying wires and discovered that they could attract or repel each other, depending on the direction of the current. Electricity, it seemed, wasn't just a one-way force. It could generate patterns in the space around it, patterns that behaved like fields. Then came Michael Faraday. Faraday's experiments were methodical, careful, and surprisingly intuitive for someone who never received formal scientific training. He discovered that moving a magnet near a coil of wire could generate an electric current. It was the mirror image of what Ørsted had seen. Instead of electricity creating magnetism, magnetism was now creating electricity. Faraday didn't have the mathematical tools to express this fully, but he had the insight. He talked about lines of force, a way to describe how the effects spread out through space, even if nothing visible connected the source to the result. Those lines would eventually become part of the modern concept of a field, but at the time they were still just a helpful way of thinking. Faraday's work was experimental, grounded in the lab, focused on what could be observed and repeated. His inventions, like the dynamo and early transformers, hinted at practical applications even before the full theory was in place. But where Faraday provided the insight, James Clerk Maxwell provided the math. Working in the mid-1800s, Maxwell brought together the known laws of electricity and magnetism into a unified framework. He took Faraday's observations and gave them a formal structure. His equations, 4 in total, described how electric and magnetic fields behave, how they influence one another, and how they can move through space. One of the most remarkable results of Maxwell's equations was the prediction of electromagnetic waves. He showed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Together, these changes could sustain each other, creating a wave that travels outward through space. And when he calculated the speed of these waves, he found it matched the speed of light. In that moment, light itself became part of the electromagnetic spectrum, no longer a separate mystery, but a natural consequence of the same laws that governed electricity and magnetism. This wasn't just an elegant result. It was a moment of deep unification in physics. Different phenomena that had once seemed unrelated, static electricity, lightning, magnetic compasses, even visible light, were now understood as expressions of the same underlying field. For the first time, people could begin to see the invisible structure that shaped so many parts of their world. The 19th century ended with a strong theoretical foundation in place, but the story didn't stop there. Experiments began to test the limits of Maxwell's theory. New parts of the spectrum were discovered: radio waves, microwaves, ultraviolet, X-rays. All of them fit into the same pattern, differing only by frequency and wavelength. And as devices were built to generate and detect these waves, the field that had once been an abstract concept became part of daily life. People learned how to broadcast sound and images across space, how to send messages without wires, how to harness energy more efficiently. The invisible was becoming practical, and the field, once a hidden force in the background, was now something engineers and inventors could use with increasing precision. Even so, the concept of the field itself remained a bit mysterious. It worked. It made accurate predictions. But what was it exactly? Was it just a mathematical tool, or something real? Physicists debated this. Some saw the field as a kind of bookkeeping system, a way to organize information about forces. Others began to think of it as something more, something physical that actually exists in space. This question would grow more important in the 20th century as new theories emerged to describe the behavior of particles, energy, and space itself. Quantum mechanics, relativity, and later quantum field theory would all lean on the idea that fields aren't just helpful, they're fundamental. But that's something we'll get to later. For now, what matters is that the electromagnetic field was no longer invisible in the sense of being ignored. It had become part of the known landscape, part of how we understood interaction, communication, and even light itself. And that shift, from strange sparks and dancing compass needles to a full-blown field theory, marked the beginning of a new kind of physics, one where influence didn't need contact, where change could ripple across space, and where what seemed empty was actually full of structure, waiting to be noticed. And once that idea took hold, it became hard to unsee. Light has always felt familiar. It pours through windows, reflects off lakes, bends through glass. We grow up learning what it does, how it lets us see, how it changes with the time of day, how it behaves differently when you shine it through a prism or bounce it off a mirror. It's one of those things that seems easy to understand because we live with it constantly. But for most of human history, what light actually is remained unsettled. Is it made of particles? Is it a wave? Is it something else entirely? We know what it feels like to look at it, to walk through it, to be warmed by it. But understanding how it moves, what carries it from place to place, took much longer to unravel. In the early days, there was the idea that light was just rays, a sort of straight-line emission that traveled from luminous objects into our eyes. That model explained some things like shadows and reflection, but fell apart when it came to subtler behaviors. Others thought of it as particles, tiny projectiles that traveled in straight lines and bounced off surfaces, and for a while, that seemed like a solid explanation. It had clarity. It felt physical. But then came the experiments that didn't fit the particle picture. When light passed through a pair of narrow slits and landed on a screen, instead of forming two bright stripes, it created a series of bands, alternating light and dark like ripples overlapping in a pond. This was interference, something only waves could do, and it suggested that light wasn't a stream of particles after all, but a wave, spreading out and interacting with itself. The interference pattern didn't make sense if light was just moving like tiny bullets through the air. It only made sense if it had peaks and troughs, phases that could add together or cancel out. That experiment and others like it pushed scientists to think differently. Maybe light was a wave, but that raised its own questions. What kind of wave? Waves usually travel through something, a medium. Sound needs air. Water waves need water. What did light move through? For a while, people imagined an invisible medium called the ether, filling all of space. But every attempt to detect this ether failed. The most famous of these, the Michelson-Morley experiment, looked for changes in the speed of light depending on the direction of the Earth's motion through the supposed ether. It found nothing. The speed of light remained constant no matter what. This was more than just a puzzle. It was a clue. The fact that light always moved at the same speed suggested it didn't need a medium at all. Instead, it moved through space itself. It was its own mechanism. The wave wasn't riding on something. It was something. And that something turned out to be the electromagnetic field. Maxwell's equations, the ones that connected electricity and magnetism into a single theory, also predicted the existence of electromagnetic waves. They described how a changing electric field could produce a magnetic field, and how a changing magnetic field could produce an electric field in turn. These two effects, cycling through each other, could propagate through space, forming a self-sustaining wave. And when the math was worked out, the speed of that wave matched the speed of light exactly. So light wasn't separate from electromagnetism. It was electromagnetism moving through space in the form of a wave, a ripple in the electric and magnetic fields traveling together perpendicular to each other and to the direction of motion. The familiar glow of a lamp, the sparkle of stars, the faint shimmer on a surface. These weren't just visual effects. They were the visible part of a larger invisible system. What this meant was profound. It meant that every time you see something, you're experiencing a field in motion. Your eyes aren't just detecting color or shape. They're reading the frequency and pattern of electromagnetic fluctuations arriving from the outside world. The sense of sight becomes a kind of field interaction. Your body, tuned through evolution, responds to these vibrations with perception. We don't see the fields directly, but we live by their signals. The visible part of the electromagnetic spectrum is actually tiny. Red light, blue light, green light. Those all fall within a narrow range of frequencies. Just above that is ultraviolet. Just below is infrared. Outside those bounds lies a vast stretch of energy we can't see, but can still detect with the right tools. Radio waves, microwaves, X-rays, gamma rays, they're all electromagnetic waves. They all share the same structure. The only thing that changes is how fast they oscillate, how much energy they carry, and how they interact with matter. When you tune a radio, you're choosing a frequency. When you heat food in a microwave, you're using a very specific band of electromagnetic waves that excite water molecules. When you get an X-ray, you're exposing your bones to high-frequency waves that pass through soft tissue but bounce off denser materials. It's all the same fundamental phenomenon, fields in motion, just tailored to different parts of the spectrum. It's easy to think of light as fast, and it is. In a vacuum, it travels at nearly 300,000 kilometers per second. But that speed isn't just a number. It's the result of how electric and magnetic fields interact. The speed of light emerges directly from the constants that define the strength of electric and magnetic forces. It's built into the structure of the field itself, and because of that, it sets a kind of cosmic speed limit. Nothing can carry information faster than light, because nothing can outrun the wave created by these fields in motion. Still, Light isn't just energy, it also carries information. Every color, every flicker, every glint of reflected light holds details about where it came from, what it bounced off of, and how far it's traveled. Stars that shine in the night sky are broadcasting electromagnetic waves across vast distances. Some of the light reaching your eyes tonight left its source hundreds or thousands of years ago. The field doesn't just move, it remembers. And it's not only the stars. Even ordinary materials interact with light in complex ways. When light strikes an object, it might be absorbed, reflected, refracted, or scattered. The specific outcome depends on the material's properties, how its electrons respond to the incoming wave. Smooth surfaces reflect light in an orderly way. Rough surfaces scatter it. Transparent materials bend light because the wave slows down as it passes through, shifting its direction. All of these behaviors are just different ways the electromagnetic field can be shaped, delayed, or redirected. Light also interferes with itself. If two beams overlap, they can combine to create a pattern of brightness and darkness. This effect, known as interference, reveals light's wave nature in clear detail. Yet in other experiments like the photoelectric effect, light behaves more like a stream of particles, knocking electrons loose from metal surfaces in a way that only makes sense if the energy arrives in discrete packets. Those packets are called photons, and they suggest a different layer to the story, one that blends waves and particles in a way that defies simple categories. But that's a topic we'll come to later. For now, what matters is the realization that light is not just what we see. It's what the electromagnetic field does when it's in motion. It's the shape that energy takes as it moves. And it's a constant presence, not just in what we observe, but in how we understand the world around us. As you sit with that, you might start to notice how much of your everyday experience depends on this one quiet fact. The soft glow of a screen. The warmth on your skin after sunlight. The way shadows shift as the day moves. All of it is field behavior. All of it is energy flowing in patterns. And even when the light is gone, the field remains, ready to ripple again, from spark to wave, from silence to motion. You might think of electricity and magnetism as opposites, one about charges, the other about poles. Electricity feels linear, like something moving along a wire. Magnetism seems more circular, looping from north to south and back again. For a long time, people treated them as separate, unrelated forces. One shocked you, the other pointed north. They came from different kinds of materials, behaved in different ways, and were explained using different tools. But as it turns out, they're not separate at all. They're deeply connected, woven into the same field, responding to each other in quiet, consistent ways that took centuries to understand. And once that connection was clear, the whole picture changed. It helps to begin with what electricity actually is. At its simplest, electricity is the movement of electric charge, most often electrons flowing through a material. When those charges are still, they create electric fields. These fields reach out into space and influence other charges nearby, attracting or repelling depending on the sign. Like charges push away from each other, opposite charges pull together. That part of the story is straightforward. Magnetism, on the surface, seems unrelated. You bring a magnet close to a paperclip and it jumps. You hang a compass from a string and the needle swings north. You sprinkle iron filings on a sheet of paper and see patterns curve around the magnet underneath. There are no obvious charges moving. Nothing shocks you, but something is definitely happening in space. Something directional, something invisible but consistent. The turning point came when people realized that magnetism isn't just its own thing. It's a consequence of moving charges. Electric current, when it flows through a wire, generates a magnetic field around it. This was the observation that Ørsted made in the early 1800s. André-Marie Ampère took it further, discovering that two parallel wires carrying current would attract or repel each other, depending on which way the currents flowed. Suddenly, magnetic effects were appearing in places where no magnets were involved, just charges in motion. So electricity could create magnetism. That was one side of the loop. The other side came from Michael Faraday. He showed that a changing magnetic field could induce an electric current in a wire, spin a magnet near a coil, or move it through the coil's center, and you'd get a voltage, a measurable push on the charges inside the conductor. Faraday's law described this relationship in simple terms. The faster the magnetic field changed, the stronger the induced current. This interplay, current creating magnetism and changing magnetism creating current, suggested that the two forces weren't just related, they were interdependent. Each one could give rise to the other under the right conditions, and that's what James Clerk Maxwell captured in his equations. He wrote down the laws that describe how electric and magnetic fields evolve in space and time, and when he combined them, he saw something unexpected, the possibility of a self-sustaining wave. Here's how it works. Imagine you have a changing electric field. According to Maxwell's equations, that field creates a changing magnetic field, and that magnetic field in turn creates a new electric field. The cycle continues. The two fields generate each other again and again as the wave moves forward through space. This is what an electromagnetic wave is, a traveling pattern of changing fields, each one sustaining the other, moving outward at the speed of light. It's a relationship based on timing and structure. If the electric field didn't change, it wouldn't produce a magnetic field. If the magnetic field didn't change, it wouldn't create an electric field. They depend on each other's motion. It's not that one leads and the other follows. It's that they oscillate together, in sync, like two dancers moving in perfect rhythm, never touching but always responding. And the effects aren't limited to open space. Inside wires and coils, similar principles apply. An alternating current, one that changes direction back and forth, generates an alternating magnetic field. That field can induce a current in a nearby coil, even if the two aren't physically connected. This is the principle behind transformers and wireless charging. The field acts as a messenger, moving energy across space without any solid bridge. It also explains why magnets work the way they do. Inside a permanent magnet, electrons aren't just sitting still, they spin. And in certain materials, those spins tend to align, creating tiny loops of current at the atomic level. Each loop produces a magnetic field, and when enough of them point the same way, the effect adds up. You get a north pole and a south pole and a field that arcs from one to the other, even outside the material itself. The magnet's influence reaches into space because the electrons inside it are constantly moving, even if the object seems still. The connection between electricity and magnetism also explains why no magnetic monopoles have ever been found. There's no such thing as an isolated north or south pole. If you break a magnet in half, you don't get a separate north and a separate south. You get two smaller magnets, each with both poles. It's different from electric charge, where positive and negative charges can exist independently. In the case of magnetism, the field always loops. And yet, the electric and magnetic sides of the field aren't completely symmetrical. They behave differently in different materials. Some substances conduct electricity easily, others resist it. Some can be magnetized, others can't. But even with those differences, the underlying link remains. The field doesn't care whether it's showing up as voltage in a wire or attraction between metal filings. The behavior might look different, but it comes from the same system. What this means in practice is that many devices we use today are built on this relationship. Motors convert electrical energy into mechanical motion using magnetic fields. Generators do the reverse, turning motion into electricity by spinning coils inside magnetic fields. Radio transmitters send out electromagnetic waves by oscillating currents through antennas. Receivers pick up those waves by detecting the tiny voltages they induce in metal components. It's all field behavior, manipulated, tuned, and put to use, and the same principles extend to nature. Lightning is an electrical discharge, but it also produces magnetic pulses that can be detected miles away. The sun's surface, roiling with plasma, creates vast magnetic structures that twist and snap, releasing bursts of energy into space. Those bursts, called coronal mass ejections, send electromagnetic waves across the solar system. If they hit Earth, they can disrupt satellites and trigger auroras in the sky. In every case, the presence of one field shapes the other. The world is full of electric currents, some natural, some artificial, and wherever those currents flow, magnetic fields form around them. The two sides of the electromagnetic field aren't just connected, they're aspects of the same underlying process. And so the idea of electricity and magnetism being separate turns out to be an illusion of perspective. What looked like two forces was really one. What felt like opposites was actually a relationship. And the more we learned about that relationship, the more we understood the field, not as a patchwork of phenomena, but as a continuous structure that responds, reacts, and moves. If you've ever seen iron filings sprinkled around a magnet, you already have a rough sense of what a magnetic field looks like, at least on the surface. The little particles arrange themselves into delicate arcs, looping from one end of the magnet to the other, curving smoothly through space. They trace out invisible paths, like threads caught in a breeze. It's one of the first visual demonstrations many people encounter in school, and even though the filings aren't actually the field, they give us a useful starting point for thinking about how the field behaves. This idea that fields can be represented with lines goes back to Michael Faraday. He imagined electric and magnetic fields as patterns of influence that could be mapped out by drawing arrows through space. Each arrow would show the direction a force would push a small test charge placed at that point. In regions where the field was stronger, the lines would be closer together. Where the field was weaker, they'd spread apart. The lines weren't meant to be literal. They were a way to picture something intangible, to give form to an interaction that otherwise had none. It's important to remember that these lines don't really exist. They're not strings floating in the air. They're a way of visualizing how the field behaves in different places, how it changes with distance, and how it wraps around or radiates from different sources. For electric fields, the lines begin on positive charges and end on negative ones, pointing in the direction that a positive test charge would move. For magnetic fields, the lines always form closed loops. They don't start or stop because there are no isolated magnetic charges. North and south poles always come in pairs. Once you accept that these lines are tools, not objects, they become incredibly useful. They help explain why field strength varies, why certain shapes of fields produce specific behaviors, and why forces act the way they do. In a uniform electric field, say, between two oppositely charged plates, the lines are straight and evenly spaced, showing a constant force across the region. In a radial field like the one around a point charge, the lines spread out in all directions, getting farther apart as they move away. This shows that the field gets weaker with distance. Magnetic fields, shaped by moving charges or intrinsic magnetic properties, form more complex loops. Around a straight current-carrying wire, the field lines form circles centered on the wire, lying in planes perpendicular to it. The direction of those loops follows the right-hand rule. If you point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field. These patterns are predictable, consistent, and mathematically describable, even if they're invisible to the eye. What's surprising, and a little elegant, is how fields interact with each other when multiple sources are present. Fields don't block or cancel each other in the way that physical objects do. They superimpose. This means that the total field at any point in space is just the sum of all the individual fields acting there. If two electric fields point in the same direction, they add. If they point in opposite directions, they partially cancel. The same goes for magnetic fields. This principle of superposition makes it possible to calculate and visualize complex field patterns by breaking them down into simpler parts. The usefulness of field lines goes beyond classroom demonstrations. They help engineers design everything from electric motors to medical imaging devices. By understanding the shape of the field, you can control how energy moves through space. You can direct it, concentrate it, minimize interference, or increase efficiency. Coils of wire are arranged in specific ways to produce strong, uniform fields inside transformers or MRI machines. Antennas are shaped to emit electromagnetic waves in desired directions. Even wireless chargers depend on the predictable geometry of fields between coils. But even as they guide design, field lines remain a kind of shorthand. In real space, the field is continuous. It exists everywhere, not just along the paths we choose to draw. Those lines are samples, not borders. The space between them is full of information too, and at any given point, the field has both a direction and a magnitude, a vector describing the force that would act on a small charge placed there. It is also worth noting that electromagnetic fields can change over time. When they do, their lines of force don't just sit still, they evolve. A time-varying electric field produces a time-varying magnetic field, and vice versa. These changes ripple outward, forming waves. The field isn't a static picture. It's dynamic, responsive. And while the lines we draw help us see the shape of the influence at a single moment, they can't capture the full richness of the motion unless we track the changes frame by frame. That's part of what makes fields such a powerful concept. They're not just forces at a distance. They're structures that occupy space. They tell us what the environment is like at every point. They give us a map of potential, of influence, of interaction. And once we learn to interpret those maps, we can make predictions, build technologies, and understand phenomena that would otherwise seem invisible or arbitrary. This way of thinking, seeing the world not just in terms of objects but in terms of fields, marks a shift in perspective. Instead of imagining particles interacting only through contact, we see them as shaping the space around them. That space, in turn, affects other particles. The result is a network of relationships guided by geometry and proximity, but not limited by touch. You might not think of your living room, your neighborhood, or the space above your head as being full of lines and loops. But in the language of fields, that's exactly what's there. The field lines aren't visible, but their effects are constant. They govern how charges move, how devices communicate, how energy flows. And whether you're standing still or in motion, whether you're holding a phone or just sitting in quiet, those invisible threads are always stretching through you and around you, linking you to the broader system. Fields aren't confined. They don't stop at the surface of an object or fade out all at once when you move a few steps away. They extend, they spread, they reach out into space with a kind of quiet consistency. Even though they don't have volume or mass in the usual sense, they leave impressions, they push and pull. And what makes electromagnetic fields particularly interesting is how they move. Not just how they exist in place, but how they transmit influence through space and time. When we think of something moving, we usually picture an object going from one spot to another. A ball rolls across the floor. A bird flies through the air. There's a start point, a path, and an end point. But with fields, what moves isn't a thing, it's a disturbance. It's a change in conditions that spreads outward, like ripples on a pond after you drop a pebble. Nothing travels with the ripple in a solid way. The water just moves up and down. But the pattern travels, and in the case of electromagnetic fields, that pattern carries energy, momentum, and sometimes information. This kind of movement is what we call a wave. And in the case of electromagnetic waves, what's waving isn't matter. It's the field itself. Specifically, it's the electric and magnetic components of the field changing over time in a coordinated way. One rises, the other responds. They build and fall in sync, forming a structure that maintains its shape as it moves forward. This structure can travel through space at the speed of light, even if the field values at any given point are always being renewed, always changing. You don't need a wire or a cable for this to happen. It can occur in empty space. And this is one of the most remarkable features of electromagnetic fields. They can carry energy across vast distances without needing any substance to travel through. The sun emits electromagnetic waves, and they cross the vacuum of space to reach Earth, bringing light, warmth, and radiation. Radio towers emit signals that move through the air, reaching antennas without anything touching in between. It's not magic. It's the property of the field, the ability to support traveling disturbances that move outward, independent of material support. The strength of a wave decreases with distance, because its energy spreads out. Like any ripple, it becomes thinner as it moves farther from its source. This is why a light bulb seems bright up close but dimmer across the room. The energy it emits radiates in all directions. The field is still there everywhere, but its intensity weakens with distance. Still, even weak fields can have an effect. Tiny changes in field strength can be picked up by sensitive detectors. That's how radio receivers work. They detect minute variations in the field caused by transmitted signals. Those variations might be in amplitude, frequency, or phase. The receiver interprets those changes and turns them back into sound or data. From the outside, it might seem like nothing is happening. But inside the receiver, circuits are responding to every shift in the field, translating invisible fluctuations into something tangible. At the core of this process is the principle that changing fields carry energy. A moving electric field generates a magnetic field. A changing magnetic field induces an electric field. And as these two components oscillate together, they form a self-sustaining wave. This isn't just a theoretical description. It's a mechanism that operates in real systems, from microwave ovens to satellite communication. It's how signals move, how power is transmitted wirelessly, how radar detects objects at a distance. The idea that fields can travel might seem abstract until you realize how much of modern life depends on it. Every text message, every wireless connection, every GPS signal is built on the premise that fields can stretch across space and carry meaning. It's not just about energy, it's about structure, how information can be encoded in patterns of change, and how those patterns can be recreated, received, and understood. But even before we harnessed these principles for technology, nature was already using them. Lightning produces radio waves that can travel thousands of kilometers. The sun's surface emits a constant stream of electromagnetic radiation, most of which we never see. And in the background of the universe itself, there's a faint microwave glow. The cosmic microwave background, left over from the early moments of the universe's expansion. It's a kind of fossilized whisper, a field still moving through space, billions of years after its origin. Fields don't move like objects. They don't need to. Their movement is more like influence traveling, a shift that spreads, a condition that propagates. And even though that movement is governed by precise rules, defined by equations limited by the speed of light, it still feels a bit strange, because it challenges the idea that everything needs something physical to push or pull. Here, space itself is active. The field exists in space, and its variations ripple outward without requiring a medium. The motion is real, even if it has no obvious carrier. This becomes especially clear when we look at how antennas work. A transmitting antenna oscillates electric current at a particular frequency. That changing current creates a changing electric field. The changing electric field produces a magnetic field, and together those changes detach from the antenna and propagate outward as a wave. The energy doesn't stay near the antenna. It moves, traveling through space in a directional pattern. Depending on how the antenna is shaped and driven, the wave can be narrow or broad, focused or diffuse, and at the other end, a receiving antenna catches that wave, not by grabbing it, but by responding to the same kind of motion. Electrons in the metal start to move in rhythm with the incoming field, creating a voltage that mirrors the original signal. This process is astonishingly efficient, especially at certain frequencies. It's what makes radio possible. It's how your phone gets a signal, even without any wires. And it's how spacecraft send images and data back to Earth from deep space. By carefully shaping and directing electromagnetic fields, using nothing but movement in circuits and precise timing. The same principles show up in optics. Lenses bend light not because they grab it, but because the electromagnetic wave interacts with the material, slowing down as it enters and speeding back up as it leaves. This change in speed alters the direction of the wave, focusing or spreading it depending on the curvature of the lens. The field doesn't bounce like a ball, it refracts, responding to the structure of the space it moves through. And when multiple waves overlap, they don't collide or interrupt each other. They superimpose. This means that the field at any point is just the sum of all the overlapping waves at that moment. Interference patterns emerge, sometimes reinforcing each other, sometimes cancelling out. This is how noise-cancelling headphones work. They detect incoming sound waves and generate new waves with the opposite phase. When the two waves combine, they cancel, reducing the overall signal. In the larger picture, this is how fields whisper through space, not in a loud, obvious way, but in subtle, structured patterns. They don't need contact, they don't need mass, they need only a change, a rhythm, and the capacity to travel. And whether it's a beam of sunlight, a radar pulse, or a satellite pinging its location, that whisper is always moving, always present. What's especially remarkable is how constant the rules are. The same principles apply whether you're dealing with a flashlight or a galaxy. The wave might be tiny or vast or somewhere in between, but the structure is consistent. The field doesn't care about scale. It behaves the same way in every part of space, across every kind of medium, under every set of conditions. And the more we understand that, the more we can use it. It might not feel like it, but your body is constantly generating electromagnetic fields, not metaphorically or loosely, but literally, through electrical activity that pulses in your brain, travels along your nerves, and keeps your heart beating in rhythm. These are not side effects or rare events. They are continuous, essential, and measurable. In fact, if they stopped, you'd know right away. Your body's electrical by design. Neurons communicate by sending tiny electrical signals along their axons. Muscle cells contract when voltage triggers calcium to flood in. The heart beats because a specialized group of cells in the right atrium fires a regular burst of current, spreading out in coordinated waves. These signals don't just move charges, they also generate changing electric fields. And whenever an electric field changes, a magnetic field appears alongside it. That's the starting point. Electricity and magnetism are linked, and they exist inside you. So the question isn't whether your body interacts with the electromagnetic field. It's how deeply it does, and how much it contributes to the field around it. Take your heart, for example. Every beat begins with an electrical impulse, an organized shift in voltage that triggers the muscle fibers to contract. This electrical pattern can be detected by placing electrodes on the skin, which is how an electrocardiogram or ECG works. It's not just a rough indicator, it's a full map of electrical activity traced beat by beat. And just as important, that activity produces magnetic field. Small, yes, but not zero. With sensitive enough instruments like a magnetocardiogram, the field can be picked up from several feet away. The same goes for the brain. Neurons fire in patterns, some fast and brief, others slow and rhythmic. The resulting electric fields are weak individually, but because they happen in large groups, their combined effect creates a magnetic field that extends beyond the skull. A magnetoencephalogram, or MEG, detects these fields using specialized sensors, offering a window into brain activity without any physical contact. These fields are so faint that they're easily masked by outside interference, but in a controlled setting, they reveal complex structures of thought, attention, and rest. The point isn't that your body's fields are strong. They aren't. The magnetic field from your heart is millions of times weaker than the one from a refrigerator magnet. But it's organized, it's rhythmic. It reflects the timing and coordination of systems that run every moment of your life. And in some cases, it's enough to influence or be influenced by fields in the environment. The body also responds to external electromagnetic fields depending on the frequency and strength. This is especially clear in medical applications. An MRI machine, for instance, uses strong magnetic fields and radio waves to align the protons in your body's water molecules, then measure how they relax back to their original state. The result is a detailed image of soft tissues generated entirely by field interactions. No cutting, no light, just a quiet negotiation between the body's molecules and the machine's magnet. Other therapies use lower strength fields. Transcranial magnetic stimulation, or TMS, delivers pulses of magnetic energy to specific regions of the brain, sometimes to disrupt patterns, sometimes to enhance them. The idea is that by changing the local field, you can influence neural behavior, at least temporarily. This isn't science fiction. It's an approved treatment for certain types of depression. The details are still being studied, but the basic mechanism is known. A changing magnetic field induces current in the brain, nudging it toward different patterns. At the cellular level, electric fields guide development, healing, and repair. Tissues seem to respond to tiny voltage gradients, directing the growth of cells in ways that aren't fully understood, but have been observed again and again. Even bone growth appears to be influenced by electric stimulation. Some implants now use small fields to accelerate healing after fractures, based on the body's apparent sensitivity to local charge changes. None of this means we're walking antennas in the same way a metal rod is. The human body is complex, wet, and electrically active in ways that don't always map neatly onto simple electronics. But the underlying principle holds. If you have moving charges, and you do, you have fields. And those fields don't stay locked inside your body. They extend into space, subtle but continuous, part of the electromagnetic environment just like every other source. Your skin, your bones, your fluids all conduct electricity to some degree. Your tissues have varying levels of resistance and permittivity. When external fields pass through you, whether from the sun, a cell tower, or a nearby appliance, they don't just bounce off. They penetrate, scatter, and sometimes interact. Most of the time, the effects are small and harmless. The field passes through without consequence, just one of many invisible influences at play. But in specific conditions, very high intensity, very low frequency, or carefully tuned therapeutic systems, those interactions can become meaningful. There's also the question of perception. Some animals, like certain birds, sharks, and turtles, can detect electromagnetic fields directly. They use them for navigation, hunting, or orientation. The exact mechanisms vary. In some cases, it's magnetite crystals in their tissues. In others, it's thought to be quantum-level interactions inside specialized proteins. Humans don't have a clear equivalent. We don't consciously sense fields the way we sense heat or sound. But there's evidence, still tentative, that our biology may be more responsive than we realize. Some studies suggest that subtle changes in magnetic fields can affect circadian rhythms, or sleep patterns, or even brainwave activity. It's hard to separate these effects from background noise, and harder still to replicate them consistently. But the possibility remains open, that the field isn't just a background condition we ignore, but a quiet influence that shapes the edge of how we feel, think, or rest. And whether or not we're aware of it, our biology is in constant motion, creating and responding to fields. Every heartbeat is a broadcast. Every neural pulse is a signal. Every breath carries with it slight electrical shifts as muscles contract and sensors adjust. You are never outside the field. You are part of it, electrically, magnetically, physically. This doesn't mean you need to worry about every wave in the air. The world has always been full of fields, from the Earth's magnetism to solar radiation, to the natural electrical activity of clouds and storms. What's new is our awareness of them, and our growing ability to measure, shape, and understand them. And as we do, we begin to see that the line between the body and the environment isn't sharp. It's porous, subtle, and alive with quiet energy. Which makes it all the more striking when you realize just how many of the objects we build, from appliances to satellites, emit their own fields too. Each one becomes a small source, a local ripple in the sea of electromagnetic motion. And taken together, they've filled our world with signals, strong, weak, pulsed, constant. Some designed, others incidental, but all of them joining the same field we're already part of. Look around any room, yours, mine, almost anyone's, and chances are it's filled with devices humming quietly beneath the surface. Screens glowing, speakers resting, phones charging, routers blinking in their corners. Even when they appear still, many of them are alive with activity. They're built to send and receive, to process, to power up, to pulse. And with each task, they stir the electromagnetic field around them, adding ripples to a space already rich with signals. Individually, each device is small. Collectively, they form a dense, layered storm of activity, quiet to the ear, but full of motion if you know how to listen. At the heart of almost every modern electronic device is the movement of electric charge. Computers, phones, kitchen appliances, they all rely on circuits, and circuits move electrons. When those electrons flow through wires, they produce electric fields. When that current changes, ramping up, switching off, oscillating in time, a magnetic field appears alongside it. These changing fields can escape the device and spread into the surrounding space, especially if the circuit isn't perfectly shielded. And since most electronics are designed to switch and pulse rapidly, the result is a flickering, low-level cloud of energy that reaches just far enough to matter. In many cases, this isn't a byproduct, it's the point. Radios and phones, for instance, are built to emit electromagnetic fields. Antennas inside these devices convert alternating current into traveling waves, which radiate into space and carry information. The pattern of the field encodes sound, video, data, packaged and sent by shifting the amplitude, frequency, or phase of the wave. On the other end, receivers detect those changes, decode them, and translate them back into something useful. None of this would work if fields didn't spread out from the source, passing through walls, air, and sometimes even parts of your body to reach their destination. But not all emissions are intentional. Many devices leak small amounts of electromagnetic energy simply because of how they operate. Any time current changes rapidly, there's potential for stray fields. The switching power supplies in laptops, the motors in refrigerators, the relays in thermostats, they all generate brief pulses of electromagnetic activity, some of which radiate outward. Engineers try to minimize this, using shielding, grounding, and filters, but the complexity of modern electronics means some leakage is inevitable. Walk through a city with the right kind of antenna, and you'll pick up a dense forest of frequencies, each one corresponding to a signal, a clock pulse, or a state change in some nearby machine. Some fields are designed to stay close. Near-field communication systems like those used for contactless payments or wireless charging operate over short distances. They rely on the tight coupling of electromagnetic fields between two coils, often just a few centimeters apart. The field doesn't travel far, but it's strong enough in that narrow zone to transfer energy or data efficiently. Other systems like Bluetooth and Wi-Fi are built to operate across rooms or buildings. Their fields are broader, less focused, and designed to work even in cluttered environments. And then there are fields that stretch much farther. Cell towers, GPS satellites, deep space transmissions, each adding their own signals to the layered field of our environment. Even simple actions trigger field changes. Flipping a light switch briefly interrupts and restores current, producing a small electromagnetic pulse. Unplugging a device creates a sharp change in the local field. Turning on an appliance often comes with a short surge as capacitors charge and motors spin up. All of these actions send momentary ripples through the surrounding space like footsteps echoing in a large hall. Most of the time, they go unnoticed. But they're there, adding texture to the ambient field. Because these devices operate at different frequencies, they rarely interfere with each other, at least not directly. Wi-Fi signals occupy a specific band, usually around 2.4 or 5 gigahertz. Bluetooth uses a similar range but with protocols to avoid overlap. FM radio is much lower, typically around 100 megahertz. GPS sits even higher, with its own carefully allocated slice of the spectrum. The electromagnetic spectrum is managed and regulated, divided into sections for different uses. This organization allows thousands of devices to operate side by side without constant collisions, like a city full of people whispering in different languages all at once. Still, interference can happen. If a signal is strong enough, or if a device is poorly shielded, unintended interactions can occur. Older audio equipment might pick up nearby phone transmissions as buzzing or clicks. Baby monitors might crosstalk with neighbors. Even car key fobs can occasionally misfire in crowded parking lots, where overlapping signals cause delays or misreads. These aren't signs of danger usually, just reminders that fields don't stay neatly inside their boundaries. They blend, they overlap, and sometimes they get a little messy. Despite the complexity, these fields are usually weak. Standing next to a Wi-Fi router or using a phone doesn't expose you to high levels of electromagnetic energy. The power involved is low, the frequencies are non-ionizing, and the duration of exposure is typically short. Most modern standards set strict limits on emissions, and devices undergo testing to ensure they stay within safe margins. The cumulative effect of so many devices is still an area of study, especially as wireless technology continues to expand. But in terms of raw field strength, the emissions from consumer electronics are minor compared to natural sources like sunlight, lightning, or even the Earth's own magnetic field. What's interesting isn't just how many devices emit fields, but how those fields carry intention. A microwave oven doesn't just heat, it uses a tuned frequency to excite water molecules. A smart speaker doesn't just sit, it constantly listens for trigger phrases, decoding audio from the waves that reach its microphones. A doorbell camera doesn't just record, it transmits, compresses, and relays video using tightly controlled signals. Each of these systems turns electrical motion into structured radiation. Each adds its own signature to the room, and each does so using the same basic principle, a changing field designed to move outward. In this way, every gadget becomes a tiny storm, not a violent one, but a consistent one, a localized source of structured motion in the electromagnetic field. Some of those storms are confined, others stretch and interact. They don't compete for space in the usual way. They layer, they ripple, they coexist. And the result is an environment shaped not just by objects, but by patterns of energy. A room isn't just full of furniture, it's full of fields, static, pulsing, drifting in and out as devices switch on and off. You might not hear them, but your body responds to them passively, absorbing a little, reflecting a little, conducting some through your tissues. You move through them without resistance, but not without presence. And as more and more devices fill the spaces we live in, the field becomes not just a background feature, but part of the structure of the world. Not fixed, not threatening, but active, textured, shaped by the tools we build and use every day. And surrounding it all, shaping it in ways we often forget, is one of the oldest and largest electromagnetic presences of all. Not made by machines, not designed by humans, but rising from deep within the planet itself. It's steady, it's slow, and it's been with us from the beginning. The Earth has its own field too, and we've been inside it all along. Beneath your feet, deep below the surface, past the crust and the mantle, and even beyond the outer core, something is turning. Not silently. Nothing in geology ever truly is, but steadily, persistently. A churning ocean of molten iron and nickel, thousands of kilometers wide, spinning in complex patterns inside the Earth. And it's this motion, liquid metal rotating under immense pressure, that creates one of the most quietly influential features of the planet, its magnetic field. You don't feel it in your day-to-day life. It doesn't tug on your phone or pull your keys across the table, but it's there, wrapping the planet in a kind of electromagnetic cocoon, stretching far into space, shielding us from radiation, and guiding everything from migrating birds to orbiting satellites. It's one of the reasons life exists here the way it does, and it's one of the oldest electromagnetic systems we know, operating long before compasses were invented, long before humans knew what a magnet even was. The Earth's magnetic field comes from the dynamo effect. The basic idea is this: when a conducting fluid moves through an existing magnetic field, it generates electric currents. Those currents, in turn, produce their own magnetic field. If the conditions are right, enough motion, enough conductivity, the right kind of turbulence, this new field can reinforce the original, creating a self-sustaining cycle. It's a feedback loop that turns the Earth's core into a planetary scale generator. No wires, no machinery, just movement, heat, and the rules of electromagnetism. The result is a field that emerges roughly near the geographic poles and arches outward into space, forming a shape called a magnetosphere. The lines of the field loop from one hemisphere to the other, curving high above the planet and plunging back in. This field interacts constantly with the solar wind, a stream of charged particles emitted by the sun. When those particles approach Earth, the magnetic field deflects most of them, steering them around the planet like a smooth shield. Without this protection, the solar wind would gradually strip away the atmosphere, just as it likely did on Mars. Some of the particles do get through, especially near the poles where the field lines dive into the atmosphere. When they do, they collide with atoms high above the surface, exciting them and causing them to emit light. This is what we see as the aurora borealis and aurora australis, the northern and southern lights, bright flickering ribbons of green, red and violet that shimmer across the sky. Beautiful, yes, but also a visible sign that the Earth's electromagnetic defenses are doing their job. The field isn't fixed. It shifts, it wobbles, and over long stretches of time it even flips. The north and south magnetic poles have reversed many times in the geological record, sometimes slowly, sometimes more abruptly. This process, known as geomagnetic reversal, doesn't happen on a schedule. The last full reversal was about 780,000 years ago. Since then, the field has wandered significantly, and measurements suggest that it's weakening gradually. That doesn't mean a reversal is imminent, but it does remind us that the field is dynamic, not a static fixture, but a living, moving part of the planet. You can see hints of this motion in the behavior of the magnetic poles themselves. The magnetic North Pole, for instance, isn't fixed at the top of the globe. It drifts year by year, currently moving from Canada towards Siberia. Navigation systems that rely on magnetic orientation, like traditional compasses, need to account for this drift. Modern tools, of course, use GPS and satellite data, but the underlying field is still there, still shaping the invisible landscape around us. In daily life, you're constantly immersed in the Earth's magnetic field. It passes through you as you walk, as you sleep, as you fly across continents. It's relatively weak at the surface, about 25 to 65 microteslas depending on location, but still strong enough to be measured and mapped. It's even used in some scientific studies to explore animal navigation. Certain species of birds, sea turtles, and insects appear to sense the field directly, using it as a kind of compass during migration. The exact mechanism remains unclear, but one idea involves tiny particles of magnetite, an iron-based mineral that can align with the field, embedded in their tissues. Another theory involves a quantum process tied to specialized proteins in their eyes. Whatever the method, the result is a kind of biological sensitivity to one of the Earth's oldest features. Humans don't seem to have a conscious magnetic sense. We don't feel the field or rely on it directly for orientation. But our bodies still live inside it, and our tools often depend on it. Some scientific instruments, like magnetometers, measure tiny changes in the field to detect underground minerals, explore archaeological sites, or even monitor space weather. Changes in the field can signal shifts in solar activity, which in turn can affect communication systems, satellites, and even power grids. In rare cases, the sun emits powerful bursts of radiation, solar flares and coronal mass ejections that slam into the Earth's magnetic field with enough force to compress it, distort it, and temporarily overload electrical infrastructure. One of the most famous examples occurred in 1859, during what's now called the Carrington event. The burst of solar energy caused auroras as far south as the Caribbean, and telegraph systems around the world sparked and failed. If something similar happened today, the impact on satellites and global communications could be substantial, and the only reason such events don't happen more often is because the magnetosphere normally absorbs or deflects that energy. So while the Earth's magnetic field might feel distant or abstract, it plays a steady role in daily life. It shields, it guides, it moves. It interacts with the devices we send into orbit and the particles that stream in from space, and it reminds us that the planet itself is a participant in the electromagnetic environment. not just a place we live, but a source of signals, patterns, and pulses. In a way, it's the original field. Long before humans built antennas or charged batteries or invented tools to measure radiation, the Earth was already radiating its presence into space. Not in visible light, not in heat, but in the slow arching curves of its magnetic lines. And those lines, even now, are part of the field we live inside every day, linking us to the sky, to the sun, and to the deeper machinery of the planet. And as it turns out, we're not the only ones tuned to this ancient broadcast. For many species, this field is more than just background. It's a sense, a signal, a way of knowing where they are and how they get where they need to go. In a world filled with landmarks, road signs, and glowing GPS signals, it's easy to forget that most living things navigate without any of that. They don't need maps or satellites. They don't plug in coordinates or check their location on a screen. And yet, somehow, they find their way. Across oceans, over continents, through empty sky and featureless sea. Birds migrate thousands of kilometers with uncanny accuracy. Whales traverse deep ocean routes that span generations. Turtles return to the exact beach where they were born. These creatures move through the world as though guided by something unseen. And increasingly, that something appears to be the Earth's magnetic field. We've known for a long time that some animals can sense direction. Homing pigeons, for instance, can find their way back to their loft from unfamiliar locations, even when released hundreds of kilometers away. Early experiments ruled out landmarks, smells, even solar position. Something else was at work, something constant, silent, and global. And researchers eventually realized that pigeons were responding to magnetic cues. Even when blindfolded or flying under heavy cloud cover, they could still orient themselves. When tiny magnets were attached to their heads, their navigation was disrupted. Birds aren't alone. Sea turtles perform remarkable migrations from nesting beaches to distant feeding grounds and back again, crossing entire ocean basins without losing their way. Laboratory studies have shown that hatchlings, fresh from the sand, already respond to magnetic fields. They swim in particular directions when placed in artificial fields designed to mimic different parts of the ocean. Somehow their internal systems are tuned not just to the direction of the field, but to its intensity and inclination, the angle at which the lines intersect the surface of the Earth. These subtle features change with location, and turtles appear to use them like coordinates on an invisible map. Salmon, too, are thought to imprint on the magnetic field near their natal rivers. After years at sea, they return to the same stream to spawn, guided in part by geomagnetic cues. Experiments with fish tanks and artificial magnetic environments have confirmed that changes in the field can alter their orientation. It's not the only sense they use. Smell plays a major role once they're close, but the field helps guide the early part of the journey, when landmarks are absent and the path stretches for thousands of kilometers. Even whales, traveling vast migratory routes through open ocean, appear to use magnetic cues. Strandings have sometimes correlated with geomagnetic anomalies, areas where the Earth's field is unusually distorted. The evidence isn't conclusive, but the pattern is suggestive. When the map changes, the route falters, and in the absence of visual cues, these creatures may be relying on the field to shape their deep-sea highways. The mechanisms behind this ability are still being uncovered. One leading hypothesis involves magnetite, a naturally magnetic mineral found in many animals. Magnetite particles can align with the Earth's field and may influence nerve cells directly. Clusters of these particles have been discovered in the upper beaks of birds, in fish noses, and in other tissues. In some species, they seem to act as tiny compasses, mechanical detectors that respond to shifts in magnetic direction or strength. Another possibility is more subtle and stranger. Some researchers believe the sense may arise from quantum effects in proteins called cryptochromes, found in the eyes of birds and other animals. These proteins are sensitive to blue light and may be involved in regulating circadian rhythms, but they also appear to respond to magnetic fields in a way that influences their chemical state. The idea is that light hits the molecule, triggering a reaction that's subtly shaped by the local field. If this is true, then some birds may literally see magnetic patterns as a kind of overlay on their vision. Not a visual image, exactly, but a sense of orientation tied to the field's direction. This sense, if confirmed, would be unlike any human perception. It's not touch, sight, sound, taste, or smell. It's something quieter, more ambient, a built-in awareness of orientation that doesn't require thought or attention. And because it's so different from our own experience, it's taken decades to uncover, let alone understand. We simply didn't know to look for it. And even now the research is ongoing. The biology is complex, the responses are subtle, but the patterns keep appearing. Different species in different environments, responding to the same field in different but reliable ways. It's not limited to animals either. Some studies have hinted that plants may respond to magnetic fields during germination and growth. Insects like bees and ants also seem to orient using geomagnetic cues, especially when foraging or returning to the hive. Even bacteria have been found to align their swimming direction with the magnetic field, possibly to navigate through sediment toward favorable oxygen levels. These responses vary in complexity and purpose, but they all suggest the same idea. The Earth's magnetic field isn't just a shield or a background condition. It's part of the sensory environment for many living things. What's remarkable is how little energy the field carries. The Earth's magnetic field is weak compared to the fields we generate with modern equipment. And yet, organisms have evolved ways to detect it with incredible sensitivity. The signal doesn't need to be strong. It just needs to be stable. And for millions of years it has been consistent enough to build a compass around, complex enough to encode location, and vast enough to guide movement across the globe. This ability may also help explain certain behaviors we've never fully understood. How monarch butterflies navigate thousands of kilometers during migration. How dogs sometimes orient themselves in particular directions before relieving themselves. How pigeons find home from faraway places. None of these behaviors can be explained by sight alone. They rely on subtle cues, sun angle, smell, memory, and increasingly, the quiet guidance of the field. And while humans don't seem to have this sense consciously, we've built our own systems to mimic it. The compass, invented centuries ago, was our first way of tuning in. Satellite navigation systems, much more recent, rely on electromagnetic signals sent from space. But the principle is the same: orientation through invisible cues. We've just externalized the ability, made it into technology, instead of growing it in tissue. Even so, we remain part of the same field. It passes through us, just as it does through birds, fish, insects, and whales. It stretches from pole to pole, touches every ocean current, and threads through every migration path on Earth. And for all the ways we've come to understand it, there's still something extraordinary about the idea that the planet is always whispering direction, quietly offering a sense of place to those who know how to feel it. And beyond direction, beyond movement, the field holds something even larger, a hidden map of the electromagnetic spectrum itself, stretching outward far past the visible into waves and frequencies we don't see, but use constantly. Because light, too, is part of this story, and in many ways it's where our understanding of the spectrum first began. You see a rainbow after a storm and it feels complete, red to violet, arcing quietly through the sky. 7 colors, maybe more if you look closely. It feels like a full picture, but that band of color is only the smallest fraction of something much larger, something we almost never see directly. Because the visible spectrum, the slice of electromagnetic waves your eyes can detect, is just a thin strip in a vast and continuous range. The rest of it surrounds you constantly, filling the air, the room, the planet. It moves through you, reflects off you, powers your devices, and carries nearly everything you know as information. This is the electromagnetic spectrum, and if light is a rainbow, then the spectrum is a hidden one that stretches endlessly in both directions beyond anything your senses evolved to perceive. At its core, the spectrum is just a way of organizing waves, electromagnetic waves, to be specific, patterns of electric and magnetic fields oscillating through space. They all move at the speed of light in a vacuum, but they do it with different rhythms. Some oscillate slowly, with long, stretched-out wavelengths. Others vibrate rapidly, their peaks close together, packed with energy. It's this frequency, how fast the wave repeats, that defines what part of the spectrum a wave belongs to. You're most familiar with the visible portion, not because it's special in physics, but because it's special to biology. Your eyes evolved to detect a narrow band of wavelengths between about 400 and 700 nanometers. That's what we call visible light, violet on the short end, red on the long. We see this range because the sun emits strongly in it, and because the Earth's atmosphere allows it through. It's a kind of natural window, tuned to the light that matters most to survival. But beyond that range, on either side, are forms of light just as real, just as structured, and in many cases far more powerful. Shift down in frequency, and you move into the infrared. These are longer waves than red light, invisible to the eye but not to the skin. You feel them as heat. When sunlight warms your arm, it's not just the visible light doing the work, it's also the infrared. Night vision cameras detect this band, turning temperature into images. Animals like snakes and some insects can see in this range, sensing prey in complete darkness. Go farther down and you reach microwaves. Not the oven necessarily, though that's one application, but the wave itself. Microwave frequencies can make water molecules vibrate, which is why they're so effective at heating food. These waves are also used for radar, satellite communication, and certain forms of data transmission. Wi-Fi lives here, as do some mobile signals. They move easily through air and can be focused into tight beams. Continue downward, and you hit radio waves. This is the longest wavelength region of the spectrum, stretching from millimeters to thousands of kilometers. These waves carry music, voice, video, text, packaged and modulated into signals that travel through buildings, through air, even through space. Radio telescopes scan this part of the spectrum to listen to the universe, capturing faint signals from distant galaxies, pulsars, and cosmic radiation. And because these waves can bend around obstacles, they're ideal for communication across rough terrain or through the atmosphere. That's one side of the spectrum, waves getting longer, frequencies getting lower, energy dropping. But head the other way, towards shorter wavelengths and higher frequencies, and the picture changes dramatically. Just above visible light is ultraviolet. These waves carry more energy than violet light, and can cause chemical changes in the molecules they hit. Sunlight contains ultraviolet radiation, and while some of it is beneficial, like triggering vitamin D production, too much can damage DNA, leading to sunburn or worse. Many insects can see in this range, detecting patterns on flowers that are invisible to us. Beyond ultraviolet are X-rays, short, high-frequency waves that can pass through soft tissue but are blocked by denser materials like bone. This is what makes medical X-rays possible. The radiation passes through your body, and a detector captures the differences, revealing the structure inside. X-rays are also used in astronomy, scanning the skies for signals from black holes, neutron stars, and superheated gas. And at the highest end are gamma rays. These waves are extraordinarily energetic, capable of breaking molecular bonds and penetrating most materials. They're produced in nuclear reactions, certain radioactive decays, and extreme cosmic events like supernovae. We don't encounter them often in daily life, at least not directly, but they shape our understanding of physics at the highest energies. The boundaries between these categories aren't sharp. They're conventions, ways of labeling regions along a continuous spectrum. The wave doesn't know it's a microwave or a gamma ray. It simply oscillates at its given frequency. And many technologies operate at the edges between categories, using parts of multiple bands to perform specific tasks. The labels are for us. The field itself is seamless. What's important is that all of these waves, radio, microwave, infrared, visible, ultraviolet, X-ray, gamma, are the same thing at the root. They're electromagnetic radiation. They differ in how they interact with matter, in how much energy they carry and what biological effects they cause. But they're all made of the same structure, a fluctuating electric field tied to a fluctuating magnetic field, both traveling together through space. Your body responds to different parts of this spectrum in different ways. Your eyes detect visible light, your skin senses infrared, your bones absorb X-rays, your cells can be damaged by ultraviolet and gamma rays, but you don't sense the full picture. Your experience of the light is partial, built around what was useful to your ancestors. The rest is there, always was, always will be. Technology has expanded your reach. Radio antennas, infrared cameras, ultraviolet sensors, X-ray machines. They've pulled pieces of the spectrum into view, extending your perception far beyond what evolution gave you. Now, we use these waves to talk, to image, to cook, to scan, to explore the universe. We bounce radar off clouds to study weather. We collect microwave background radiation to understand the early universe. We map gamma-ray bursts from billions of light years away. And perhaps most strikingly, all of this, every part of the spectrum, is just the field, behaving differently. Light isn't a substance. It's what the electromagnetic field does when it moves. The color, the heat, the radio signal, they're all expressions of the same field, just at different speeds. In the end, the rainbow is wider than you think. And though your eyes only see a sliver, your world runs on every part of it. From the slow roll of radio to the high pitch of gamma rays, the field is full, continuous, and endlessly expressive. And once you start to see that spectrum, not just the visible one, but the whole, the idea of light changes. It stops being just a glow. It becomes a language, one that carries heat, signal, structure, and time itself in waves that never stop. You use it constantly, even if you've never thought about it. You wake up to an alarm that syncs to atomic time via a signal broadcast from hundreds of kilometers away. You tap your phone and data streams in over invisible channels. Your car unlocks as you walk up to it. Your thermostat senses your presence. Your Bluetooth headphones pair without a wire in sight. All of this happens through the field, specifically through carefully structured electromagnetic signals designed to travel, to interact, and to carry information. And yet, most of the time, you don't see the field, you don't feel it. It's part of your environment the way air is part of it, constant, unnoticed, and essential. It begins with communication. Almost every wireless system you rely on, from texting to navigation to streaming, runs on the manipulation of electromagnetic waves. These systems encode information by changing the properties of a wave, its amplitude, its frequency, its phase. A transmitter sends the modified wave into space, and a receiver tuned to that frequency picks it up and interprets the signal. The wave itself doesn't carry language or images, it carries patterns, structure. The shape of the change is what holds meaning. Wi-Fi, for instance, operates in a specific slice of the microwave spectrum. A router takes digital data, emails, websites, video, and converts it into signals that pulse through the air at gigahertz frequencies. Your device receives those pulses, translates them back into usable content, and delivers them to your screen. This happens billions of times per second in real time, across short distances, in a narrow band of spectrum. And because it's electromagnetic radiation, it doesn't need wires. It spreads through space, bending around corners, bouncing off walls, fading with distance. Cellular networks do the same thing, but across wider areas. Cell towers transmit and receive electromagnetic waves that carry voice, text, and data. Each phone call is a stream of modulated waves, bouncing between antennas, routed through fiber lines, connected to distant endpoints. GPS satellites orbiting the Earth constantly emit precise timing signals, tiny pulses of electromagnetic radiation that your phone interprets to determine your location. The field acts as a carrier, a bridge, a clock. Even objects you don't think of as electronic can participate. Contactless credit cards use short-range electromagnetic fields to transmit your account data to a payment terminal. The same principle powers key fobs, smart locks, toll passes. Wireless charging pads generate oscillating fields that induce current in nearby devices. No plug, no direct contact, just energy moved through a shared portion of the field. Sensors, too, depend on it. Radar uses reflected waves to detect objects and measure speed. LiDAR, used in autonomous vehicles, emits pulses of light and measures how long they take to bounce back, building a 3D map of the environment. Medical imaging systems like MRI use strong magnetic fields and radio waves to visualize internal tissues. Remote controls send infrared pulses. Satellite dishes pick up weak microwave signals from orbit. All of these tools work by sending, shaping, or receiving waves in the field. And while most of this happens invisibly, the effects are concrete. Traffic lights change based on magnetic loops embedded in the pavement. Warehouse robots navigate using low-frequency signals from floor beacons. Hearing aids adapt in real time using wireless audio links. Even your electric toothbrush uses inductive charging, an application of alternating fields that never physically touch. What makes this possible is precision. The field itself is continuous and everywhere, but the systems we build operate in narrow slices tuned to very specific parameters. A Bluetooth headset doesn't pick up FM radio. A satellite dish doesn't respond to Wi-Fi. Each device listens only to its band, its format, its signal. And because the spectrum is shared, it's carefully managed. Regulatory bodies allocate frequencies for different purposes to minimize interference, creating a kind of layered architecture of signals, each stacked on the others without blending. But that layering only works because the field itself can handle it. It doesn't get full. It doesn't jam unless signals overlap in time and frequency. It simply adds everything together. Every ripple, every pulse, every wave. And at each point in space, the field reflects the sum of everything happening nearby. That sum might be simple. The glow of the sun, the whisper of the Earth's own magnetism. Or it might be complex. Dozens of signals crisscrossing a city block, bouncing from walls, slipping through glass, absorbed and re-emitted by devices large and small. This passive presence of the field makes certain technologies possible that would seem impossible otherwise. Radio telescopes scan for signals so faint that they're drowned out by a phone circuitry. Quantum sensors detect magnetic field shifts at the atomic level. Scientists look for gravitational waves by measuring how light waves change over kilometers of vacuum tube. All of it rests on the assumption that the electromagnetic field can be manipulated with precision and that it can carry subtle shifts without distortion. And because the field moves at the speed of light, it's not just useful, it's fast. Fast enough to allow nearly instant communication around the planet. Fast enough to synchronize stock markets, to coordinate rescue operations, to connect people in real time across oceans. The waves aren't slowed by borders. They don't care about terrain. They respond only to physical properties, permittivity, permeability, absorption. And once you know how to shape them, you can build systems that work almost anywhere. But it's not just the global systems that matter. Even inside a single home, the field is busy. Your smart thermostat senses your phone's proximity using low-power radio waves. Your TV remote speaks in infrared. Your baby monitor transmits audio in a reserved slice of spectrum. And your oven, your fridge, your doorbell, all of them, increasingly, connect not through wires, but through the field. This quiet architecture of connection is now so embedded in daily life that it often goes unnoticed. The technology fades into the background. The router disappears behind the shelf. The signal indicator becomes a bar on a screen. And yet, the field does all the heavy lifting. It moves the data. It synchronizes the time. It powers the tools. It brings the network alive. Even nature uses the field without seeing it. Lightning is a sudden redistribution of electric charge, producing both light and radio waves. The ionosphere, an electrically active layer of the atmosphere, bends and reflects radio waves, enabling long-distance transmission. Plants use light, another part of the field, to drive photosynthesis. Animals tune into magnetic fields to migrate. All of this happens without language, without measurement, without even awareness. The field is just used. And as more systems go wireless, the pattern grows denser, the signals become more complex, and yet the field continues to carry it all, layered, silent, structured. It's infrastructure without cables, motion without contact, and in most cases, you never see it. You just tap the screen and it works. And for all this precision and power, the field has one more trait that makes it remarkable. It scales. The same equations that describe a local Bluetooth chip also describe the waves emitted by a pulsar. The same field that carries your music also carries light from the stars. It doesn't change with distance, only your ability to shape it does. And that ability, refined, extended, scaled up, is what led to something even stranger. The understanding that electromagnetic waves don't just carry signal, they carry energy. Energy that can be harvested, focused, and used, even when it's coming from something as small as the glow of the sky. When most people think of electromagnetic fields, they picture the faint ambient kind, the invisible glue of wireless signals, the subtle warmth of sunlight, the quiet buzz of daily electronics. These are fields we live with comfortably, fields that hum beneath the surface of things. But that picture leaves something out. Because fields aren't always faint, they're not always gentle. Under certain conditions, they can become focused, amplified, and extraordinarily powerful. And when they do, they stop whispering and start pushing, bending, even breaking the structures around them. The difference is scale and purpose. Consider the transformer, a standard piece of infrastructure sitting in substations and utility poles, converting high-voltage electricity into usable power for homes and businesses. It works by applying the principles of electromagnetic induction. When alternating current passes through one coil of wire, it creates a changing magnetic field. That field moves through a second coil, inducing a current there. The stronger the original current, the stronger the resulting field. And in heavy industrial settings, these fields are anything but weak. They can generate enough force to lift train cars, melt metal, or erase magnetic storage just by proximity. Step into a power plant, and the presence of the field becomes hard to ignore. Generators spin coils of wire through powerful magnetic fields, producing massive amounts of electricity. The scale is different, but the underlying physics is the same as what powers your phone charger. It's just more intense, more current, more motion, more concentrated energy moving through space via the electromagnetic field. The result is a controlled force, shaped by coils and circuits, turned into grid-scale power. But not all strong fields are static or industrial. Some are pulsed, short-lived, and intensely focused. Microwave ovens, for instance, use high-frequency electromagnetic waves, around 2.45 gigahertz, to excite water molecules in food. The field doesn't heat the food directly. It causes the molecules to vibrate, and that vibration produces thermal energy. The result is fast, targeted heating. And while the waves are confined to a metal chamber, the field inside is strong enough to cook in minutes what would otherwise take much longer. Lasers offer another example. A laser is just light, electromagnetic radiation, in a narrow band of the visible or infrared spectrum. But because it's coherent, meaning all the waves are aligned in phase and direction, the electromagnetic field it produces can be incredibly concentrated. At high power, laser light can cut steel, vaporize materials, or even trigger nuclear fusion in laboratory settings. It's not a different kind of field, it's just one shaped with extraordinary precision. In laboratories, researchers push the field even further. Particle accelerators like the Large Hadron Collider use electric and magnetic fields to guide particles at speeds approaching the speed of light. Those fields must be strong, stable, and precisely timed. Without them, the particles would veer off path or never reach collision speeds. In fusion experiments, magnetic confinement is used to trap plasma at temperatures hotter than the sun's core. Here, fields aren't just tools, they're containers, shaping matter itself to hold the impossible. There are natural sources of powerful fields too. The Earth's magnetic field is relatively modest at the surface, but in space, especially near the poles, it interacts with solar storms in ways that can generate bursts of electromagnetic energy strong enough to disrupt satellites and power grids. Lightning is another example, a sudden, massive discharge of electricity that produces a local field strong enough to ionize air, split trees, and induce current in distant wires. The electromagnetic pulse, EMP, from a lightning strike can damage electronics that aren't even in the direct path. And in the universe, far beyond Earth, the scale becomes staggering. Neutron stars, remnants of collapsed massive stars, can spin rapidly while carrying magnetic fields trillions of times stronger than anything we can create on Earth. Some of these stars, called magnetars, have surface fields so intense that they can distort the structure of atoms. Their bursts of radiation, traveling through space as high-energy electromagnetic waves, can be detected from light years away. What's common across all these examples is the role of field strength. Weak fields carry information. Strong fields carry energy. And when that energy is concentrated by design or by nature, it can change the physical state of matter. It can ionize atoms, tear electrons free from their orbits, align magnetic domains, or compress plasma into fusion conditions. The difference isn't in the kind of wave, it's in the amplitude, the frequency, the structure. The same physics, just turned up. These strong fields also change how devices are built. Shielding becomes essential. Metal enclosures to contain fields, grounding paths to safely dissipate energy, filters to block unwanted frequencies. Medical imaging machines like MRIs rely on huge magnets and precisely timed radio pulses. Anyone entering the room must remove metal objects, not because the field is dangerous in itself, but because it's strong enough to pull loose objects at high speed or interfere with implanted electronics. High-voltage transmission lines, too, produce noticeable fields. Walk beneath them and you might hear the faint crackle of corona discharge, the sound of electrons ionizing the air. You might even feel a faint tingling if you touch a metal fence nearby. The field isn't harmful in most cases, but it's present, strong enough to influence nearby conductors and shaped by the scale of the system. In controlled settings, we use strong fields for precision and power. We focus them, modulate them, contain them. But when fields grow too strong without control, they become disruptive. Interference, overload, noise. This is why sensitive electronics require shielding, why cables are twisted or insulated, why environments are regulated to avoid unintended emissions. The field, at high strength, is not just signal, it's influence, and it doesn't always stay within its assigned bounds. Still, the power of strong fields isn't something to fear, it's something to understand, because the same force that can erase a hard drive or lift a steel beam is also what keeps your data safe, your machines running, your body functioning. It's a question of context, of how the field is shaped, guided, applied. And once you begin to recognize that the difference between a signal and a force is often just a matter of scale, the field becomes even more interesting. It's not passive, it's active. And when shaped with enough care, it can do more than carry energy. It can carry structure, create order, even influence matter at the smallest scales. Because fields, when strong enough, stop simply describing the world and start changing it. Are we surrounded by too much EM? It's a fair question, maybe even an inevitable one. When you live in a world packed with wireless signals, blinking routers, 5G towers, satellite networks, electric cars, smart appliances, and an ever-expanding web of connected things, it's hard not to wonder, are we surrounded by too much electromagnetic radiation? Is all of this invisible activity harmless? Or are we quietly bathing ourselves in something we don't fully understand? The concern usually centers on man-made sources, radio towers, cell phones, Wi-Fi, Bluetooth, power lines. None of these existed just a few generations ago. Now they're everywhere, and they're always on, transmitting, receiving, pulsing in carefully designed frequencies to carry everything from text messages to satellite telemetry. It feels new, unnatural, intense, but intensity is relative. And when it comes to electromagnetic fields, strength matters far more than presence. The field has always been there. The sun, after all, emits more electromagnetic radiation in 1 second than every device on Earth combined. You're constantly bathed in visible light, ultraviolet and infrared. Lightning produces bursts of radio waves. The Earth's own magnetic field wraps around you from birth to death. What's changed isn't the existence of fields, it's the way we use them and the scale at which we generate them. To assess whether we're surrounded by too much, you have to separate types of electromagnetic radiation. Not all waves are created equal. They all follow the same rules, oscillating electric and magnetic fields moving through space. But their effects on matter differ dramatically depending on frequency and energy. Non-ionizing radiation includes radio waves, microwaves, infrared, and visible light. These are the fields we use for communication, heating, lighting, imaging. They don't have enough energy per photon to break chemical bonds or ionize atoms. They can heat materials, yes. That's how a microwave oven works, but only at high intensities and with focused energy. Your Wi-Fi signal or phone call doesn't come anywhere close to those power levels. Ionizing radiation, on the other hand, includes ultraviolet, X-rays, and gamma rays. These have enough energy to knock electrons off atoms, break DNA strands, and cause biological damage. The risks of ionizing radiation are well documented. They depend on dose, duration, and proximity. Too much UV from sunlight increases the risk of skin cancer. Excessive X-ray exposure, if uncontrolled, can be harmful. Gamma rays, thankfully rare at ground level, are even more potent. So when people worry about too much M, they're usually thinking about non-ionizing radiation. Fields that are technically harmless in terms of direct molecular damage, but still provoke concern because of their ubiquity, their invisibility, and the fact that we don't fully experience them. It's not that we feel unsafe, it's that we don't know what we're feeling at all. Over the years, countless studies have tried to answer whether low-level electromagnetic fields from man-made sources pose health risks. Research into cell phone usage, for example, has looked at everything from brain activity to cancer incidents. The consensus among major health organizations like the World Health Organization, the FCC, and the National Institutes of Health is that there's no conclusive evidence linking typical exposures to significant health effects. Phones, routers, towers, all of them operate at power levels well below safety thresholds, and those thresholds are set conservatively, with large margins to account for unknowns. But the studies continue, and the concerns persist. Part of that comes from scale. Even if the field strength is low, the number of sources is high. You might carry several transmitting devices on your body. You walk through a cloud of overlapping signals every time you enter a public space. And the more we rely on wireless systems, the more crowded the spectrum becomes. There's also the issue of long-term exposure. Many technologies are too new for full generational studies. What happens when someone spends 80 years surrounded by low-power radiation? How does constant but mild stimulation affect sleep, development, attention? The answers aren't always clear, and even when the risk is low, people may feel uneasy simply because they can't opt out. The field is ambient. It's everywhere. You don't have to engage it for it to be present. There are also rare cases of electromagnetic hypersensitivity. Individuals who report symptoms like headaches, fatigue, or dizziness in the presence of certain devices. Scientific studies haven't consistently confirmed a link between these symptoms and exposure levels. In double-blind tests, people often can't tell whether the field is present or not, but the symptoms are real, even if the cause remains debated. And the discussion raises a broader point. Perception matters, even when the physics suggests safety. Engineering plays a role too. Devices are tested for emissions, limits are imposed, shielding is built in, protocols are designed to minimize unnecessary exposure. A phone doesn't transmit at full power unless it needs to. Routers scale down when idle. Smart systems negotiate signal strength in real time. All of this reduces the footprint of artificial fields in daily life. And yet, the environment is still full of motion, full of waves, full of overlapping systems using the same fundamental physics for everything from unlocking doors to detecting earthquakes. So are we surrounded by too much? It depends on what you mean. In terms of raw field strength, the answer is likely no, at least not from typical regulated sources. In terms of density, maybe. In terms of our ability to measure and manage the complexity, we're still learning. The field has become a platform for everything, and our relationship with it is only getting deeper. The important distinction is between energy and information. The vast majority of modern electromagnetic emissions carry signal, not heat. They're structured to convey meaning, not deliver power. And while the intensity is low, the precision is high. It's not that your phone is trying to flood the room with radiation. It's aiming to talk quietly to a single device a few meters away. The field is shaped, focused, efficient, but even quiet signals accumulate. The environment is never still, and that raises questions, not just about health, but about stewardship. How do we design systems that coexist? How do we ensure our spectrum remains usable, clear, and safe? How do we monitor interference, redundancy, overload? Because the field isn't just a medium anymore, it's a shared space. And as with any space, the way we fill it matters, not just in terms of risk, but in terms of balance, between power and subtlety, between connection and control. And perhaps the deeper question isn't whether there's too much, but whether we're paying enough attention, not just to what we're emitting, but to what we're building. The field will carry what we give it. It always has. The challenge is making sure what we give it is worth the signal, and that we continue to understand the system we now live inside. Your brain runs on electricity, not the kind that powers machines, but a subtler version, organized across billions of cells constantly shifting. Every thought, memory, sensation, and action you experience is tied to the coordinated firing of neurons. When those neurons fire, they move charges, and wherever charges move, fields follow. This isn't metaphor, it's physics. Every time your brain acts, it generates electric and magnetic fields. But the interaction doesn't stop there. Under the right conditions, the process can work in reverse. Fields can influence the brain too. This idea, shaping brain activity using electromagnetic fields, isn't science fiction or a fringe theory. It's real, studied, and in some cases used clinically. It doesn't involve surgery. It doesn't inject chemicals. It works through modulation, applying precisely timed fields from outside the body and letting them interact with the currents already flowing inside. Sometimes the goal is to quiet things down. Sometimes it's to stimulate. Sometimes it's just to observe. The most common method is called transcranial magnetic stimulation, or TMS. In a typical setup, a coil is placed near the scalp. When a strong pulse of current flows through the coil, it creates a changing magnetic field. That field passes through the skull and induces a small current in the underlying brain tissue. The effect is temporary and localized, like nudging a system already in motion. Depending on the parameters, TMS can increase or decrease the likelihood that nearby neurons will fire. Clinically, TMS is approved in several countries as a treatment for major depressive disorder, especially in cases where medication doesn't help. Repeated sessions, delivered over days or weeks, can alter the brain's electrical rhythms in ways that appear to improve mood, regulate thought patterns, or shift attention. It doesn't work for everyone. The biology is still being explored, but the mechanism is solid. Electromagnetic induction applied to the brain, reshaping activity without cutting or implanting anything. There are other approaches too. Transcranial direct current stimulation, or TDCs, uses a weak, constant electric current delivered through electrodes placed on the scalp. Unlike TMS, it doesn't rely on magnetic fields. It delivers the electric field directly. The idea is that by slightly altering the resting potential of neurons, making them a bit more or less likely to fire, you can influence how brain networks behave. The effects are more subtle than TM's, but the equipment is simpler and the risks are low, at least at typical settings. Some studies have looked at even lower field strengths, comparable to the fields generated naturally by the brain itself. These methods, often experimental, aim to interact with the brain's rhythms without overpowering them. They don't inject energy so much as guide timing, and because brain activity is rhythmic, organized into waves of various frequencies, these techniques try to synchronize with those rhythms. Slow waves during sleep, faster waves during attention or movement. Each has its own signature, and each, in theory, can be shifted using external cues. This leads to ideas like entrainment, using weak periodic fields to align internal brain rhythms to an external pattern. It's similar in concept to pacing a runner with a metronome. You don't force the stride, you just offer a reference. Over time, the system adapts. In practice, entrainment can be achieved with light, sound, or direct electrical stimulation. It's been studied in relation to sleep enhancement, attention control, memory consolidation, and even treatment of neurological disorders. What makes the brain particularly sensitive to these techniques is its balance of structure and fluidity. It's not a single machine. It's a network, a constantly reconfiguring set of circuits, tuned by activity, chemistry, and external input. And because the signals that drive it are small, measured in millivolts and microamperes, they can, in some cases, be nudged by small changes in the surrounding field. But there are limits. The skull, skin, and fluids around the brain resist and scatter electrical currents. Reaching specific areas with precision is difficult. The effects are often weak and hard to isolate, and individual differences, anatomy, health, genetics, can lead to wide variation in outcomes. What works for one person may not for another, and the long-term effects of repeated stimulation are still being studied. Still, the principle stands. Fields can influence the brain, and under the right conditions, those effects can be meaningful. Researchers are exploring applications for epilepsy, Parkinson's disease, schizophrenia, anxiety, chronic pain, and more. Not all of these are clinically validated, but the interest is growing, because the promise is clear. A non-invasive way to change how the brain functions, not with drugs or surgery, but with fields. What's even more striking is how close this is to what the brain already does. Neurons produce fields as they fire. Networks generate oscillations. Brainwaves, as measured by EEG, reflect large-scale coordination across regions. The entire system is electrical and dynamic, and so it makes sense that it can be shaped by tools that speak the same language. This isn't about mind control or reading thoughts. It's about modulation, slight adjustments to a system that's already active. It's not precise in the way that a drug targets a receptor, but it's fast, adjustable, and potentially reversible. And because it works through physics rather than chemistry, the risks of systemic side effects are often lower. There are still open questions. What's the optimal frequency for a given condition? How long should stimulation last? How do we tailor it to individual brain patterns? And perhaps most importantly, how do we ensure that the benefits outweigh the costs ethically and medically? But the broader message is this: the brain is both a generator and a receiver of fields, and as we learn more about how those fields shape its activity, we're gaining new tools, not to override thought, but to support it, not to replace consciousness, but to explore its rhythms. And in a world increasingly filled with electromagnetic signals, it's not hard to imagine a future where some of those signals aren't just for communication or control, but for tuning the self gently from the inside out. There's a moment, if you dig far enough into the nature of fields, where things stop behaving the way you expect. Up until then, the electromagnetic field is familiar, even comforting. It ripples, it flows, it carries light and heat and signal. It's the medium through which almost everything moves. But beneath that classical layer, under the surface of the smooth, continuous field, there's something stranger, something noisier, more uncertain. And that's where quantum electrodynamics begins. Quantum electrodynamics, or QED, is the theory that describes how light and matter interact at the smallest scales. It takes the idea of the electromagnetic field and breaks it down, not into waves and lines, but into probabilities and virtual exchanges. In this view, the field isn't just a smooth background. It's alive with constant fluctuation. Even in perfect vacuum, even with no light, no charge, no particles moving, there's still activity. The vacuum isn't empty. It never was. This sounds like contradiction. How can nothing contain motion? How can a vacuum, which by definition holds no particles, be full of anything? The answer comes from quantum mechanics. In the quantum world, emptiness is unstable. Uncertainty is built in. You can't simultaneously know the exact energy and the exact duration of a system. And that uncertainty means that the energy of the electromagnetic field never truly settles at zero. It jitters, not wildly but persistently. This jittering shows up as vacuum fluctuations. Tiny, temporary changes in the field that spontaneously appear and disappear. They're not particles in the traditional sense. They're not even real in the classical sense. But they have effects. They can shift energy levels. They can change the behavior of atoms. And they've been measured indirectly with extreme precision. One of the most famous demonstrations of this is the Casimir effect. Take two uncharged, perfectly conducting plates and place them a few micrometers apart in a vacuum. Classically, nothing should happen. But quantum electrodynamics predicts a force between the plates, not from particles or heat or any known classical source, but from the difference in vacuum energy on either side. The space between the plates excludes certain wavelengths of fluctuation. Outside the plates, more wavelengths are allowed. The result is an imbalance, and the plates are gently pushed together. The effect is small, but real. It's been measured, and it's a sign that the vacuum isn't truly empty. It has structure, pressure, activity. A constant whisper of virtual photons appearing and vanishing, never directly observable, but always present in the equations. These virtual photons aren't limited to strange lab setups. They're fundamental to how charged particles interact. In QED, when one electron repels another, it does so not by sending out a continuous force, but by exchanging virtual photons. These are force carriers, not real particles flying through space, but temporary blips in the field, existing just long enough to transmit momentum. They don't appear in detectors. They don't leave tracks. But their cumulative effect is measurable. It's how light interacts with matter, how atoms form, how fields talk to each other. Even the fine structure of atomic energy levels, the tiny shifts that define the spectrum of hydrogen, for example, can be traced to vacuum fluctuations. In one case, known as the Lamb shift, measurements showed that certain energy levels were slightly off from what classical theory predicted. The explanation required quantum corrections, adjustments based on the subtle, constant jitter of the field. The same logic extends outward. Empty space at the quantum level is a seething baseline. Every point contains potential, not just in electromagnetic terms, but in every field: gravitational, nuclear, scalar. Quantum field theory treats each particle not as an object, but as a localized excitation of its field. An electron is a bump in the electron field. A photon is a bump in the electromagnetic field. And the vacuum is where all those fields live, even when they appear still. This has implications beyond physics labs. In cosmology, for example, vacuum energy is tied to the concept of dark energy, the mysterious pressure that seems to be accelerating the expansion of the universe. Quantum field theory predicts a vacuum energy far larger than what we observe, leading to one of the great unsolved problems in theoretical physics. We know the vacuum has energy. We just don't know how much or why it acts the way it does on cosmic scales. In more practical terms, the field's quantum nature limits how precisely we can measure it. Even in a perfect instrument, there's a noise flaw, an irreducible jitter caused by the uncertainty baked into the vacuum itself. Engineers account for this in sensitive electronics, especially in cryogenic systems or quantum computers. The vacuum can't be silenced. It always hums. This humming isn't something you'd notice. It doesn't warm your skin. It doesn't trigger detectors unless you go looking with the right tools. But it matters. It defines the boundary between the possible and the impossible. It sets the baseline for how stable atoms are. It shapes how particles decay, how signals travel, how time itself unfolds at small scales. And it also raises questions. If the vacuum is always active, what does nothing really mean? If empty space has structure, is it ever truly empty? Can we manipulate it, tap into it, create fields from it? These aren't hypothetical ideas. Research into zero-point energy, energy associated with the lowest possible state of a field, continues, though practical applications remain speculative. But even without exotic technologies, the fact remains, the electromagnetic field doesn't begin with motion, it begins with potential. With the constant low-level fluctuation that defines every moment, even when nothing seems to be happening. And in that fluctuation is a kind of foundation, a whisper of structure, not a signal, not a wave, just the field being itself in its quietest possible state, never still, never silent, and always ready to move. Inside every atom there is tension. Not visible tension, not something you'd see if you zoomed in with a microscope, but an invisible, constant push and pull that keeps the whole structure intact. At its core is a nucleus, protons and neutrons packed tightly together, and around it, a cloud of electrons, lighter by orders of magnitude but no less essential. The atom stays whole not because it's solid, but because of a field. The electromagnetic field doesn't just let the atom exist, it's the reason atoms have any shape at all. Think of it this way. Electrons don't orbit the nucleus like tiny planets around a sun. That model is a simplification, a way to visualize something more abstract. What actually holds electrons in place is the attraction between opposite charges. The protons in the nucleus are positively charged, the electrons are negative, and that attraction isn't just a tendency, it's an electromagnetic force. It's the field pulling on the charges, shaping their distribution, holding the atom together from the inside out. But unlike gravity, which only pulls, the electromagnetic force pushes and pulls depending on the charges involved. Opposite charges attract, like charges repel. This dual nature adds complexity, and it's that complexity that defines the structure of matter. For example, electrons don't collapse into the nucleus because of another principle layered on top of the field: quantum mechanics. In quantum terms, electrons aren't tiny dots circling a center. They're wave functions, distributions of probability, and those wave functions are shaped by the electromagnetic potential around the nucleus. The field determines how tightly an electron is bound, how likely it is to be found at a certain distance, what energy levels it can occupy. Each level is a solution to the equations that govern both the field and the quantum behavior of particles. This is where chemistry begins. Every interaction between atoms, every bond, every reaction, relies on these quantum electromagnetic rules. When atoms combine to form molecules, it's the field that allows electrons to shift and settle into shared configurations. Covalent bonds, where electrons are shared, ionic bonds, where electrons are transferred, metallic bonds, where electrons drift among many nuclei, all of them are electromagnetic at their root. The field defines the landscape, and the electrons respond. Without this structure, matter wouldn't have texture, solids wouldn't resist pressure, liquids wouldn't hold shape, your hand wouldn't stop when it pressed against a wall. What keeps one object from passing through another isn't solidity in a classical sense, it's the electromagnetic field. When the electrons in your hand approach the electrons in the wall, they repel each other. Not because the electrons know anything, but because the field around them doesn't allow them to occupy the same space without energy. That repulsion is what gives matter its firmness. The same field determines how light interacts with matter. When a photon, a particle of light, strikes an atom, it can be absorbed, reflected, transmitted, or scattered. All of these outcomes depend on how the photon's energy matches the energy differences between electron levels. If the match is right, the electron absorbs the photon and jumps to a higher state. Later, it may fall back and emit a photon of its own. Color, transparency, reflectivity. They're all outcomes of how matter's electrons respond to the electromagnetic field and its fluctuations. Even heat, in many cases, is a result of field-based motion. When atoms vibrate, when molecules collide, the movement of charges generates tiny electromagnetic disturbances, infrared radiation that spreads outward. You feel this as warmth. It's not just kinetic energy being transferred, it's the field radiating the consequences of motion. Zooming out, the structure of the periodic table reflects this invisible architecture. The rows and columns aren't arbitrary. They describe how electrons fill specific orbitals, regions shaped by the electromagnetic field's potential and the rules of quantum behavior. Each element behaves the way it does, reactive, inert, metallic, insulating, because of how its electrons are organized and how those electrons are held in place by the field. Even exotic forms of matter obey this logic. Superconductors, which allow current to flow without resistance, do so because of special arrangements of electrons and their interactions with lattice structures, again mediated by the electromagnetic field. Semiconductors, which form the basis of modern electronics, depend on how electrons can be nudged through energy bands shaped by internal fields. In both cases, the key is control, not of matter, but of how matter responds to the field. And then there's plasma, the so-called fourth state of matter, where electrons are stripped from atoms entirely, leaving a soup of ions and free charges. Here, the electromagnetic field becomes more dynamic, more visible in its influence. Plasmas twist and pulse in response to external fields, forming structures that look almost alive. The sun is a plasma. So are neon signs and lightning bolts. Without the field, these wouldn't behave as they do. They'd just be chaos. So when we talk about atoms, we're really talking about fields, not just the presence of charges, but the space around them, the influence, the shape, the rules. The electromagnetic field isn't a layer added on top of matter. It's the scaffolding that lets matter exist. And when you press your fingers together and feel resistance, what you're feeling isn't solidity. It's exclusion. It's the field saying, this far, no farther. And if the field disappeared, if somehow you could turn it off, atoms wouldn't just rearrange. They would dissolve. Electrons would fall into nuclei. Chemistry would stop. Molecules would lose their shape. Light wouldn't interact with matter. The universe wouldn't burn out or freeze. It would lose structure entirely. But the field doesn't disappear. It persists. And every solid, liquid, gas, or plasma you've ever seen owes its existence to the quiet, constant tension of attraction and repulsion that plays out across the empty spaces within and between atoms. Not as a surface feature, but as the defining principle of what matter even is. Space isn't empty. Not really. It may look like a cold vacuum, dotted with stars and crossed by lonely light. But beyond the silence is structure, fields, stretching endlessly, invisible but real. The cosmos isn't just made of matter and motion. It's woven with fields that shape galaxies, ignite stars and guide particles on paths we only began to trace in the last century. And among those, the electromagnetic field is one of the most influential. It doesn't just operate on the scale of atoms and circuits. It reaches across light years, threading its way through the universe itself. Start with stars. They're not just balls of gas. They're plasma, charged particles in constant motion. And wherever charges move, they create magnetic fields. Every star, including our sun, has a magnetic structure. Loops and arcs, waves and pulses, sometimes calm, sometimes violent. Sunspots are magnetic storms. Solar flares are sudden reconfigurations of magnetic fields, hurling charged particles across the solar system. These particles ride waves of electromagnetic energy, shaped by the sun's field and distorted by their own motion. It's not just heat and light that travel from the sun. It's information carried on a field, spiraling outward, sometimes arriving here as bursts of geomagnetic activity that dance across polar skies. Beyond the sun, other stars behave similarly, but at greater scale and intensity. Some rotate rapidly, generating magnetic fields thousands of times stronger. Pulsars, which are spinning neutron stars, emit beams of electromagnetic radiation with clock-like regularity. They're often compared to cosmic lighthouses, sweeping their beams through space, blinking on and off as they spin. Those beams come from particles accelerated along magnetic field lines, whipped into motion by fields so strong they can trap energy for thousands of years. Magnetic fields also shape the galaxies themselves. Spiral galaxies like our own Milky Way contain coherent magnetic structures, fields that twist with the arms of the galaxy, influencing the motion of interstellar gas and dust. They don't dominate gravity, but they play a role in how matter clumps, how stars form, how cosmic rays move. We see their imprint in polarized light, in radio emissions from distant regions, in the subtle alignment of dust grains that tell us how the field is flowing across vast distances. And between galaxies, the field continues. Intergalactic space isn't as empty as once thought. It contains particles, plasma, radiation, and electromagnetic fields stretched thin across incomprehensible distances. These fields are faint, but they guide charged particles, bending them subtly over millions of light years. Cosmic rays, high-energy particles flung out from supernova, black holes, and other energetic events, travel through these fields. Their paths aren't straight. They spiral, curve, scatter. The field doesn't stop them, but it shapes their motion, alters their arrival, scrambles their origin. Even now, we struggle to trace their exact sources, in part because the field has curved their trajectories across the universe. In galaxy clusters, the story gets more intense. These are regions filled with hot plasma and tangled magnetic fields, stretched and compressed by collisions between galaxies. As the clusters merge and evolve, their fields are amplified, creating enormous structures that radiate in radio frequencies. Some of the largest electromagnetic structures we've detected aren't stars or planets, or even black holes. They're relic fields, echoes of ancient collisions, glowing faintly across clusters of galaxies. Black holes, too, are wrapped in fields. Despite the name, they don't simply consume everything. Many of them emit powerful jets, streams of plasma shot out at nearly the speed of light, extending for thousands of light years. These jets don't come from the hole itself, but from the disk of material spiraling into it. Magnetic fields in the disk twist and coil, launching particles along the poles in tightly focused beams. The energy involved is staggering, and all of it is tied to the interaction between gravity, rotation, and electromagnetic fields. Even the early universe bore the mark of the field. In the cosmic microwave background, the faint afterglow of the Big Bang, we detect polarization patterns that hint at primordial fields. Tiny asymmetries in the radiation point to forces active when the universe was barely formed, when matter and radiation were still entangled, and the first structures were beginning to emerge. These clues are faint, but they suggest that fields were there from the beginning, shaping the expansion, influencing the distribution of matter, guiding the earliest flows. Today, we study these fields with telescopes that see in more than visible light. Radio observatories scan the sky for synchrotron radiation, light emitted by charged particles spiraling through magnetic fields. X-ray satellites watch hot gas trapped by field lines. Instruments aboard spacecraft measure solar wind, detect shifts in polarity, track the boundaries where the sun's influence fades and interstellar space begins. And all of it, every distant flare, every field line, every cosmic echo, follows the same physics that governs a simple bar magnet on a desk. The same equations describe the sun's corona and a household coil. What changes is scale, energy, context. The field is the same. The universe simply uses it on a grander canvas. This doesn't mean the field explains everything. Gravity still holds galaxies together, dark matter still shapes structure. But the electromagnetic field is the most expressive. It lights up the sky. It connects distant regions. It carries energy and signal and structure across vacuum and time, from the smallest charge to the largest jets. And in all of this motion, in all of this distance, the same principle holds. A charge in motion creates a field. A field creates force, and force creates shape. Stars pulse, galaxies spiral, space itself glows, not because of matter alone, but because the field is always there, wrapping around motion, responding, guiding, and recording the path of every moving particle, not as background, but as part of the fabric itself. You don't see it. You don't hear it. There's no taste, no scent, no weight to it in your hand. And yet the electromagnetic field is always with you. Not occasionally, not just when you switch on a light or scroll through your phone, but constantly. From the moment your cells begin to form to the last quiet flicker of activity in your brain. It isn't just part of the environment, it is the environment in ways most people never think about. Start with biology, the beating of your heart, the firing of neurons, the transmission of signals through your nervous system. None of this happens without electric charge. Your cells maintain gradients of ions, potassium, sodium, calcium across their membranes. They use pumps and channels to shape those differences, and when the time comes, they let the charges move. The flow is brief, controlled, and crucial. It generates voltage, and with it, a field. When a neuron fires, it doesn't just send a signal down its length. It alters the electric field in the tissue around it. That shift, though tiny, is real. It's what electroencephalograms detect, a rolling pattern of electrical activity that reflects your brain's rhythms. Awake, asleep, focused, dreaming. Each state has its own frequency, its own signature. And while we often describe these in terms of waves, they're ultimately field effects, not metaphor, not symbolism, physics. Your muscles respond to these fields too. Your heart's rhythm is controlled by electrical impulses. Each beat begins with a field change. Medical devices like electrocardiograms record those shifts. Defibrillators reset them when they fail. The entire system is electrical, and because moving charges generate magnetic fields, you also produce those, weak but measurable, even outside your body. Magnetoencephalography, or MEG, is a technique that records the brain's magnetic fields directly. It's sensitive enough to pick up the fields generated by synchronized neuron firing down to the millisecond. It doesn't require electrodes on the scalp. It just watches the field from nearby. And that field, as it turns out, is unique to you. Not like a fingerprint, but like a rhythm. Your brain's internal conversation, rendered not in words but in electromagnetic motion. The field also shapes how your senses work. Vision begins when photons, tiny packets of electromagnetic radiation, strike molecules in the retina. The energy of the photon shifts the configuration of a protein, starting a cascade that your brain interprets as light. Hearing, while mechanical at first, becomes electrical as soon as hair cells in the ear convert vibrations into signals. Touch, taste, smell. Each ends in the same place, electrical pulses, guided through nerves, shaped by fields. Even the way your body interacts with technology is mediated by fields. The touchscreen on your phone responds to the electric field around your fingers. Biometric sensors track electrical signals from your skin. Implants and prosthetics rely on electrodes that read or deliver pulses. Some experimental therapies use low-power fields to stimulate healing, guide cell growth, or influence brain function. These aren't invasive or chemical. They're just modulated fields shaped to match the body's own language. And language in this case means structure. Cells aren't just collections of molecules. They're organized systems with polarity, charge separation, field gradients. Even inside a single cell, electric fields guide the motion of particles, the shape of organelles, the direction of growth. In development, these patterns matter. The way a limb forms, the way nerves grow, the way tissues organize, all have electrical components. It's not the only force involved, but it's part of the blueprint. There's also the environment. You live inside a field bigger than yourself. The Earth's magnetic field surrounds you, subtle but stable, guiding migratory animals, shielding the planet from solar radiation. That field passes through you, through buildings, through every living thing. It's weak compared to artificial sources, but it's ancient, and for some organisms, essential. Even bacteria can align with it. Some research suggests that human cells respond to weak fields under certain conditions, though the effects are still being explored. What's clear is that the electromagnetic field isn't something separate from you. It's not a utility or a tool. It's embedded in your biology, your chemistry, your perception. When your heart beats, when your thoughts form, when your skin senses heat or your eyes catch light, it's the field at work, quietly, efficiently, without pause. And yet, we rarely think about it. We talk about the body as if it's just tissue and fluids, bones and organs. But remove the fields, and none of it works. Communication fails. Motion stops. Sensation disappears. The field is what links parts into systems, is what gives life its tempo, its signal, its direction. There's no off switch. You're always emitting, always sensing, always moving through a web of fields that you help create. And that web isn't isolated. It overlaps with the world's larger structures, the electricity and power lines, the signals in the air, the background light of the universe. You're not separate from those either. You reflect them. You absorb them. Sometimes you even depend on them. So when we talk about the electromagnetic field, we're not just talking about something external. We're talking about a force that shapes us silently, from within. Not dramatic, not glowing, not cinematic, just consistent, reliable, fundamental. You don't need to feel it to be shaped by it. And the fact that you don't notice it most of the time, that it works without attention, without permission, might be its most extraordinary quality. Not because it hides, but because it never stops. It is quite literally the background of being. You've been living in it the whole time, not beside it, not near it, not occasionally touched by it, but inside it. The electromagnetic field isn't a layer that sits on top of reality, it's part of the structure. It defines how light moves, how atoms hold together, how your brain thinks, how a message crosses the planet. It doesn't need your awareness to function, but the moment you become aware of it, the world shifts. Things you thought were empty turn out to be full. Connections that seemed abstract, between your body and the sun, between a star and a signal, between memory and motion, reveal themselves as consequences of the same rules, the same field, the same invisible pattern that ripples across a screen and across the cosmos. It's not magic, it's not mystical, it's just the logic of interaction, written in fields instead of words. And whether you're sending a message, watching a sunset, touching metal, thinking a thought, or standing perfectly still, it's always there, wrapping you, shaping you, carrying everything that moves, including you. No wires required.